The comet crosses the frost line somewhere beyond Jupiter's orbit, where sunlight weakens to a pale suggestion and temperatures hover near the threshold where water remains solid for billions of years. It has no name yet in the old sense, no mythological claim, no poet's christening, only the designation 3I Atlas, a catalogue entry noting its hyperbolic trajectory and interstellar origin. The 3I marks it as the third confirmed interstellar object detected passing through the solar system, a wanderer unbound by the sun's gravity, following a path shaped by forces exerted light-years away and eons ago. Atlas refers to the automated survey telescope in Hawaii that first registered its motion against the background stars, a patient machine watching the sky for objects that do not belong to familiar orbits. It arrives from the direction of the constellation Ursa Major, though such designations mean little to a body that has travelled through the space between stars. Its velocity, measured at roughly 40 kilometers per second relative to the Sun, exceeds the escape velocity of the solar system, confirming what spectroscopy and orbital calculation already suggest. This is no native child of the Sun's planetary disk, no fragment of the Kuiper belt nudged inward by slow perturbations. It formed elsewhere, in a protoplanetary disk circling a star whose light has never been identified, condensing from gases and ices in molecular clouds that predated the Sun's own birth. Only took 4.5 billion years to arrive here, give or take a few million. The nucleus measures perhaps 3 kilometers across, a modest size for a comet, but enormous by human scale, a mountain of ice tumbling through darkness, its surface blackened by cosmic radiation and micrometeorite bombardment accumulated during its passage through interstellar space. That surface crust, dark as charcoal, insulates the interior, preserving volatiles in a state largely unchanged since the comet's formation. Water ice dominates the composition, but ammonia hides within the matrix, along with methane, carbon monoxide, carbon dioxide, and trace organics molecules forged in the cold chemistry of stellar nurseries, where temperatures never rise above a few dozen degrees above absolute zero. The ice remembers pressures and conditions that no longer exist, holding information about the galaxy's chemical state in an epoch before Earth's oceans or Mars's rivers ever pooled beneath alien skies. As 3I Atlas crosses into the inner solar system, sunlight begins its slow work of transformation. Photons strike the dark crust, depositing energy that penetrates micrometer by micrometer, warming layers that have known only the coldness of the void. Sublimation starts at the surface, water ice transitioning directly from solid to gas without passing through liquid phase, a process the comet has performed countless times in other stellar systems, around other suns whose names are unknown. Gas molecules escape the nucleus, carrying dust grains with them, and the comet begins to develop a faint coma, a diffuse atmosphere of liberated volatiles that scatters sunlight and makes the object visible to telescopes monitoring near-Earth space. The coma expands slowly at first, a tenuous shell around the nucleus, growing as the comet falls deeper into the Sun's gravitational well. Jupiter's gravity bent the comet's path centuries ago, an interaction so subtle that the comet itself experiences no awareness of the deflection, merely follows the curvature of space-time dictated by the gas giant's immense mass. That gravitational assist altered the trajectory by a fraction of a degree, enough to aim the comet toward the orbit of Mars rather than sending it past Venus or into the outer system's scattered disk. The math governing this deflection is elegant and deterministic. Newtonian mechanics expressed in differential equations that predict, with remarkable precision, where the comet will be at any given moment. No mystery attends the physics, only the question of why this particular comet, among countless billions in the Oort cloud and beyond, happened to pass through this particular corridor of space at this particular time. The universe offers no answer, only the fact of arrival. Mars waits ahead in its orbit, a rust-coloured world 17 months into its 22-month journey around the Sun. Positioned along the ecliptic plane, where the comet's trajectory will bring the two bodies into proximity. Ground-based observatories have tracked both objects for months, calculating the geometry of their encounter with increasing precision as new data refines orbital parameters. The closest approach will occur in late April, during Martian northern spring, when the polar ice cap sublimates and dust storms begin to stir in the southern highlands. No collision appears likely. The probability calculations hover near 0.003%. A statistical whisper, but the passage will be close enough to alter the comet's path slightly, to allow detailed spectroscopic study and to add microscopic amounts of cometary dust to Mars's thin atmosphere, close enough to matter, perhaps, in ways that unfold over centuries rather than hours. The comet does not hurry. It falls sunward at speeds that seem extraordinary by human measure, but represent only the gentlest acceleration across astronomical distances, velocity accumulated over months and years as gravity performs its patient work. 40 kilometers per second sounds swift until one calculates how long such speed requires to cross even the modest gap between Jupiter and Mars, weeks turning into months. The comet shrinking and growing alternately in telescopes as its distance shifts and its coma expands. Ice sublimates continuously now, the nucleus losing mass at a rate measured in tons per second, material that will never return to the solid body, never recondense in the cold of interstellar space. This passage through the inner solar system represents an ending of sorts. The comet will exit transformed. Lighter, its crust thinner, its ancient volatiles partially spent. Still, the ice endures beneath the darkened surface, in layers protected from direct sunlight. Water molecules remain locked in crystal lattices formed before the sun existed. Organic molecules, simple chains of carbon, hydrogen, nitrogen, oxygen persist in the frozen matrix, relics of circumstellar chemistry that produce the building blocks of life, not through intention, but through the blind statistics of molecular collision in cold clouds. If the comet carries amino acids or nucleobases, they sleep in darkness, neither living nor dead, merely structured arrangements of atoms awaiting conditions that might or might not permit them to participate in biochemistry. Mars will receive a portion of this material in a few weeks' time, dust settling onto polar ice and equatorial regolith, adding infinitesimal contributions to the planet's inventory of organics. Whether that matters, whether Mars still harbours chemistry complex enough to recognise such gifts, remains uncertain. The solar wind pushes against the expanding coma, ionising gas molecules and creating a faint ion tail that streams away from the sun, invisible to human eyes but detectable in ultraviolet wavelengths, where oxygen and carbon emissions glow faintly. The tail points always away from the sun, not back along the comet's trajectory, a demonstration of radiation pressure overcoming the comet's inertia. Dust particles, heavier than ions, form a separate tail that curves gently, following the comet's orbital path, a ghostly arc visible in telescopes as scattered sunlight. Both tails grow longer as the comet approaches perihelion, reaching lengths measured in millions of kilometers, structures so vast they dwarf the nucleus itself, yet composed of material so diffuse that a human could pass through them without noticing. Only took a mountain of ice to paint such enormity across the sky. NASA tracks the comet through multiple instruments, ground telescopes in Chile and Hawaii, the Hubble Space Telescope during gaps in its observation schedule, and Mars orbiters preparing to turn their cameras toward the visitor. Data accumulates in quiet archives, spectral lines indicating composition, photometric measurements tracking brightness variations, astrometric positions refining the orbit. No press releases accompany these observations, no dramatic announcements of danger or discovery. The comet is catalogued, measured, understood within the framework of cometary science developed over centuries of patient study. Its interstellar origin makes it noteworthy, but not unprecedented. Oumuamua passed through in 2017, Borisov in 2019, and theoretical models predict such visitors arrive several times per year, most too faint to detect. The silence surrounding 3i Atlas reflects not secrecy, but routine. The normal rhythm of planetary science proceeding without fanfare. The comet continues falling toward Mars, indifferent to observation, following the path dictated by gravity and momentum. Its ice sublimates, its coma expands, and somewhere ahead, a red planet waits in the ancient patience of worlds that have watched such visitors for 4 billion years. The nucleus rotates slowly, completing one full turn every 11 hours and 40 minutes, a rhythm established perhaps during its formation in a distant protoplanetary disk, or altered by collisions in the dense environment of its birth cloud, or modified by outgassing jets that act as tiny rockets, changing the spin through asymmetric sublimation. No one knows which forces shape this particular rotation, only that telescopes detect periodic variations in brightness as different faces of the irregular nucleus turn toward the Sun. The rotation is not smooth precession causes the axis to wobble slightly, a motion that will take decades to fully characterize, though by then the comet will have long since departed the inner solar system. Astronomers note the wobble in technical papers, adding it to models of cometary dynamics that attempt to explain how such bodies maintain structural integrity across billions of years. Beneath the blackened crust, ice exists in layers not uniform like manufactured materials but stratified, mixed, interspersed with dust grains and rocky particles accumulated during formation. The water ice is not pure H2O but contains isotopic variations. Some molecules carry deuterium instead of regular hydrogen, a ratio that tells stories about temperature and environment during condensation. The deuterium to hydrogen ratio in 3i Atlas differs slightly from that of solar system comets, a subtle signature suggesting formation in a molecular cloud with different thermal history or chemical enrichment. Such ratios are measured in parts per 10,000. Yet they reveal distinctions across light years and eons, tiny differences that persist in frozen archives, waiting for spectroscopes to read them. Ammonia hides deeper in the nucleus, mixed with water ice in proportions that suggest condensation at temperatures near 70 Kelvin, cold enough that ammonia remains solid, contributing to the structural matrix that gives the comet its shape. As sunlight penetrates the surface and warming reaches these ammonia-rich layers, gas escapes through cracks and fissures in the crust, creating localized jets that spray material into space at velocities exceeding the nucleus's escape velocity. These jets emerge from specific locations, active areas where the crust is thin or fractured, and they rotate with the nucleus, sweeping through space like lighthouse beams made of sublimating ice. The jets carry dust with them, silicate grains smaller than human cells, carbonaceous particles rich in organic compounds, fragments of minerals that condensed in the cooling envelope of a dying star before being incorporated into the comet's structure. Carbon monoxide ice, even more volatile than water, begins sublimating while the comet still lies beyond Jupiter's orbit. Carbon monoxide requires temperatures only slightly above absolute zero to transition directly to gas. It is the most eager to escape, the first to respond to the faint warming of distant sunlight. By the time through us Atlas crosses into the inner solar system, most of its carbon monoxide has already departed, though reservoirs remain protected beneath insulating layers, waiting for fractures to expose them. When carbon monoxide does escape, it does so violently, expanding rapidly and potentially disrupting surrounding material, a process that can cause cometary outbursts. Sudden brightenings visible from Earth as the coma temporarily fills with fresh gas and dust. No such outburst has occurred yet, but the possibility remains as the comet approaches perihelion. Methane exists in trace amounts, frozen into clathrate structures where water molecules form cage-like lattices trapping individual methane molecules. These clathrates are stable at low temperatures but decompose as warming proceeds, releasing methane in discrete pulses rather than continuous streams. The chemistry of clathrate formation and decomposition remains incompletely understood. Laboratory experiments can reproduce the structures, but the conditions in a tumbling comet nucleus, with varying temperatures, pressures, and compositions defy simple modelling. Scientists observe the effects methane emission lines in spectra, brightness variations correlating with rotation, and construct hypotheses about subsurface processes that may or may not accurately reflect reality. The comet keeps its internal workings private, revealing only what escapes through the surface. Carbon dioxide ice forms a distinct layer or perhaps scattered pockets within the nuclear spectroscopy, cannot yet resolve the three-dimensional structure, only infer composition from emissions. Carbon dioxide sublimates at temperatures intermediate between carbon monoxide and water, creating its own contribution to the expanding coma. The gas molecules, once free, absorb ultraviolet light and fluoresce at specific wavelengths, allowing astronomers to map the distribution of CO2 around the nucleus and calculate production rates. Current observations suggest the comet releases approximately 500 kilograms of carbon dioxide per second, an amount that sounds substantial but represents an infinitesimal fraction of the nucleus's total mass. At this rate, the comet could continue outgassing for thousands of orbits around other stars before exhausting its volatile inventory, though no orbit returns it to warmth once it leaves this solar system. Organic molecules compose a significant fraction of the non-ice material complex carbon chains formed through radiation chemistry and icy mantles coating interstellar dust grains. These organics include formaldehyde, methanol, hydrogen cyanide, and more complex species whose precise identification requires high-resolution spectroscopy. Some molecules detected in cometary comae match those found in the interstellar medium, confirming that comets preserve pristine samples of the galaxy's chemical reservoir. Other molecules appear to form during the comet's warming, created as sublimating gases undergo photochemistry and sunlight new compounds, synthesized from ancient ingredients. Chemistry occurring in the diffuse coma that never happened in the frozen nucleus. The boundary between preserved and newly created molecules is not always clear. Dust grains number in the trillions, each one a microscopic archive. Some grains are crystalline silicates, olivine and pyroxene minerals formed at high temperatures, perhaps in the atmospheres of dying stars or in the hot inner regions of protoplanetary disks, later transported to cold outer regions where they incorporated into comets. The presence of such high-temperature minerals in a body formed in extreme cold represents one of the quiet paradoxes of planetary formation materials, born in fire preserved in ice, mixed through processes that operated across the breadth of a forming stellar system. Other grains are amorphous, lacking crystalline structure, possibly formed through direct condensation in cold molecular clouds. Still others are carbonaceous rich in organic compounds, opaque and dark, giving the nucleus its low reflectivity. The nucleus loses perhaps 10 tons of material per second now, a rate that will increase as the comet nears Mars and sunlight intensifies. 10 tons per second sounds catastrophic in human terms, but barely registers at cometary scales. The nucleus contains trillions of tons of material, enough to sustain this mass loss for decades of continuous activity without noticeably shrinking. The lost material spreads through the inner solar system, some of it escaping entirely, some of it gradually spiraling inward toward the Sun, some of it following orbits that will eventually intersect planetary atmospheres. Mars will collect a portion dust settling through the thin air, water molecules photodissociating and adding hydrogen and oxygen atoms to atmospheric chemistry. Earth receives cometary dust constantly, a gentle rain of extraterrestrial material that amounts to thousands of tons annually across the planet's surface, invisible and unnoticed except by scientists collecting samples from polar ice or ocean sediments. The coma now extends several 100,000 kilometers from the nucleus, a tenuous cloud of gas and dust maintained by continuous sublimation. Sunlight ionizes molecules within the coma, stripping electrons and creating a population of charged particles that interact with the solar wind. The solar wind, a stream of charged particles flowing outward from the sun's corona, carries its own magnetic field, and when this field encounters the cometary ions, complex electromagnetic interactions result. The comet develops a bow-shocker boundary where the solar wind deflects around the obstacle presented by the coma, slowing and compressing as it encounters increased particle density. The bow shock is invisible but measurable, a demonstration of magnetohydrodynamics operating on scales too vast for human intuition, yet governed by equations that fit on a single page. Inside the coma, collisions between molecules remain rare despite the apparent density. The coma is vacuum by terrestrial standards, containing perhaps a few thousand molecules per cubic centimetre, compared to the trillions present in Earth's atmosphere at sea level. Yet this near emptiness glows faintly as molecules absorb sunlight and re-emit at characteristic wavelengths. Hydroxyl radicals, OH molecules created by water photodissociation, emit strongly in ultraviolet wavelengths, creating a vast invisible envelope around the nucleus. Neutral oxygen atoms, also products of water destruction, emit a greenish light visible in sensitive instruments. The coma is not inert but chemically active, a laboratory where photons drive reactions that disassemble ancient molecules and create new species never present in the frozen nucleus. The comet carries no memory of its formation, no record accessible to internal experience. It is not conscious, not purposeful, merely an assembly of matter following physical law. Yet in another sense it carries profound memory, isotopic ratios recording the temperature and density of its birth cloud, organic molecules preserving chemical pathways active in the early galaxy, crystalline structures encoding thermal histories across billions of years. Memory exists not as experience but as structure, information written in the arrangement of atoms, readable by those with instruments and patience. The ice knows nothing and remembers everything. A contradiction resolved only by recognizing that knowledge requires awareness, while memory requires only persistence. Mars draws closer in the comet's trajectory, still weeks away but present in orbital calculations that predict the encounter with increasing certainty. Mars hangs in its orbit at 1.5 astronomical units from the Sun, a distance that places it beyond the inner edge of the habitable zone by most conventional definitions. Though what constitutes habitability remains a moving target in planetary science. The planet completes one orbit every 687 Earth days, tracing an ellipse more eccentric than Earth's nearly circular path Mars approaches, within 206 million kilometres of the Sun at perihelion, and recedes to 249 million kilometres at aphelion, a variation sufficient to create seasonal differences more pronounced than those caused by axial tilt alone. Currently, Mars occupies a position along its orbit where northern hemisphere spring transitions slowly towards summer, the polar caps sublimating carbon dioxide ice and exposing underlying water ice that will persist through the warmer months. The planet rotates once every 24 hours and 37 minutes, a rhythm nearly synchronized with Earth's, though arrived at independently through the physics of planetary formation and angular momentum conservation. That rotation, measured precisely by tracking surface features, reveals a world turning at steady pace, unperturbed by the massive moon that slows Earth's spin through tidal friction. Mars has no large moon, only Phobos and Deimos, two small captured asteroids that exert negligible tidal influence. Without such braking, Mars has maintained its rotation rate across billions of years, though subtle variations occur as the planet's moment of inertia shifts with seasonal redistribution of atmospheric carbon dioxide between polar caps and air. The atmosphere wraps the planet in a layer averaging about 10 to 20 kilometres thick. Though boundaries are imprecise in the thin Martian air, pressure at the surface measures roughly 600 pascals, less than 1% of Earth's sea level pressure, creating an environment where water cannot exist as stable liquid under current conditions. The atmosphere consists of 95% carbon dioxide, with nitrogen and argon comprising most of the remainder, along with trace amounts of oxygen, carbon monoxide, water vapour, and noble gases. This composition differs dramatically from Earth's nitrogen-oxygen mixture, reflecting Mars's smaller mass and weaker gravity, which allowed lighter gases to escape to space over geological time, while heavier carbon dioxide lingered. Dust suspends permanently in the thin air. fine particles of iron oxide and silicate minerals that give the sky its characteristic butterscotch hue even on clear days. The dust particles measure typically 1 to 3 micrometers in diameter, small enough to remain aloft for months, large enough to scatter visible light efficiently. During global dust storms, which develop every few Martian years when conditions align during southern summer, the atmospheric dust loading increases dramatically. Temperatures rise at altitude while cooling at the surface, and the entire planet becomes shrouded in a haze that obscures surface features even in powerful telescopes. No global storm currently rages. The regional dust devils leave dark tracks across bright terrain as they remove fine material and expose darker substrate. The southern highlands dominate half the planet's surface, ancient cratered terrain elevated several kilometers above the northern lowlands, a dichotomy whose origin remains debated in planetary geology. Some researchers favor an impact hypothesis. A massive collision early in Martian history excavated the northern basin, creating the elevation difference and possibly disrupting the planet's internal dynamics. Others propose endogenous explanations involving mantle convection patterns that produced asymmetric crustal thickness. The southern highlands preserve craters from the late heavy bombardment, a period roughly 3.9 billion years ago, when the inner solar system experienced intense meteorite impacts as gravitational perturbations scattered debris from the outer planets inward. Those ancient craters, some exceeding 1,000 kilometers in diameter, record an epoch of violence that reshaped every rocky world from Mercury to the asteroid belt. Hellas Basin marks the southern highlands, an impact structure so vast and deep that atmospheric pressure at its floor exceeds 800 pascals, creating conditions marginally more hospitable than the higher terrain. The basin formed when an asteroid or comet nucleus perhaps 100 kilometers across struck Mars with energy equivalent to billions of nuclear weapons, vaporizing impactor and target rock, excavating crust to depths, exposing mantle material, sending ejecta around the planet. The impact would have temporarily created a molten zone, perhaps even a transient atmosphere of vaporized rock, conditions lasting perhaps decades before cooling restored solid surfaces. Now the basin holds only dust and seasonal frost, the violence of its creation erased by 4 billion years of wind and sublimation, readable only in the circular ring of mountains that marks the crater rim. Olympus Mons rises 21 kilometers above the surrounding plains, the tallest planetary mountain in the solar system, a shield volcano constructed through countless eruptions over billions of years. The volcano likely last erupted a few 100 million years ago, though dating Martian surfaces remains imprecise without sample return missions. Lava flows cascade down its flanks in overlapping sheets, each flow recording an episode of magma reaching the surface through the planet's cooling crust. The volcano's base spans 600 kilometers, an area comparable to Arizona, yet the slopes rise so gently that standing on them would not reveal the immensity. The grade averages only 5 degrees, barely perceptible to human senses. The height accumulated across such vast horizontal distance that perspective fails to convey scale. The planet's core remains partially molten. Seismic data from InSight lander suggests a liquid iron core extending perhaps 1,800 kilometers from the planet's center, smaller relative to planetary radius than Earth's core, but sufficient to have once generated a magnetic field. That field collapsed roughly 4 billion years ago, when core cooling reached a threshold where convection ceased and the dynamo shut down. Without magnetic protection, the solar wind began directly interacting with the upper atmosphere, stripping ions to space, gradually eroding the thick early atmosphere that had maintained warmer conditions and stable liquid water. The process continues today at rates measured in tons per hour, unnoticeable on human timescales but devastating across epochs, transforming Mars from a possibly habitable world to the cold desert observed now. Ancient river valleys carve the southern highlands, branching networks resembling terrestrial drainage systems, evidence that water once flowed across the surface in quantities sufficient to erode rock and transport sediment. These valleys formed primarily during the Noachian period, roughly 4 billion years ago, when atmospheric pressure may have supported liquid water and precipitation. The valleys show characteristics of both rainfall-driven erosion and groundwater sapping, suggesting a hydrological cycle operated for at least episodic periods. Though whether Mars sustained continuous wet conditions or experienced only brief warm intervals between longer cold-dry epochs remains contested. The valleys now lie empty, their channels filled with dust. Their role as conduits for water ended billions of years before life on Earth evolved beyond single cells. Gale Crater holds the Curiosity rover. Dormant currently in Martian night, its systems powered down except for essential heating to protect electronics from temperatures dropping below -70°C. The rover has traversed this crater for over a decade Earth time, analysing rocks that record environmental transitions from ancient lake sediments to wind-blown deposits, finding evidence of past habitable conditions but no definitive biosignatures. The crater sits in the northern mid-latitudes, a position that will place it roughly beneath the comet's trajectory during closest approach. Though beneath means little, when the comet passes at altitudes exceeding 40,000 kilometers higher than the orbits of both Martian moons. Phobos orbits at only 6,000 kilometers altitude, completing 3 orbits per Martian day, gradually spiraling inward through tidal interactions that will cause it to either crash into Mars or break apart into a ring system in approximately 50 million years. The Moon measures 27 kilometers across its longest axis, a misshapen potato of rock and regolith, probably a captured asteroid from the main belt, though its orbit lies almost perfectly equatorial, complicating capture scenarios. Its surface is dark, reflecting only about 7% of incident sunlight, covered in dust estimated to be 100 meters deep in places, accumulated over billions of years from micrometeorite impacts and its own slow disintegration. Phobos has witnessed every comet that has approached Mars since its capture, a silent observer without capacity for memory or record. Its craters the only testament to eons watching visitors pass. Deimos orbits farther out at 23,000 kilometers, above synchronous orbit altitude, which means it orbits more slowly than Mars rotates, causing it to rise in the west and set in the east as seen from the surface. Smaller than Phobos at only 15 kilometers across, Deimos is even darker, its regolith perhaps mixed with carbon-rich material from the outer solar system. Both moons will witness the comet's passage from perspectives unshared by any human eye, Phobos seeing it sweep past at relative velocities that would blur details into streaks, Deimos watching from greater distance as a point of light growing marginally brighter before fading again toward background stars. The planet waits, if waiting can be attributed to a world without intention. It orbits, rotates, sublimates frost, circulates thin atmosphere, slowly loses hydrogen to space where solar ultraviolet splits water vapor into hydrogen and oxygen. The hydrogen, lighter, escapes more readily, while oxygen either reoxidizes surface minerals or escapes more slowly. Over billions of years, this process has removed an ocean's worth of water, the hydrogen lost to space, the oxygen locked in rust that colors the soil. Mars does not anticipate the comet, does not prepare or brace it, simply continues the processes that have defined it since its formation, indifferent to visitors, unchanged by observation, a world obeying physics without awareness that physics contains it. The geometry of celestial mechanics unfolds with mathematical precision, 2 bodies following paths determined by gravitational fields, initial velocities, and the distribution of mass throughout the solar system. The comet's trajectory, a hyperbola open at one end, intersects the imaginary sphere of Mars's orbital path at an angle calculated to 3 decimal places by software running in observatories scattered across Earth's surface. Mars moves along its ellipse at an average velocity of 24 kilometers per second, though currently travelling slightly slower as it climbs away from perihelion toward the more distant portions of its orbit. The comet approaches at 40 kilometers per second relative to the Sun. But relative to Mars, the frame of reference that matters for close approach calculations, the velocity difference measures approximately 32 kilometers per second. a closing speed that will carry the comet from beyond lunar orbit distance to closest approach in less than 2 hours. Closest approach will occur on April 27th at 14 hours, 32 minutes universal time, plus or minus 6 minutes, depending on final refinements to the comet's position as tracking continues. At that moment, the comet will pass 47,000 kilometers from Mars's center, or roughly 44,000 kilometers above the surface, a distance equal to about 1/10 the span between Earth and its moon. In astronomical terms, this represents an extraordinarily close passage. Comets typically pass planets at distances measured in millions of kilometers. Their trajectory is bent only slightly by gravitational interaction. This encounter brings the comet well within Mars's gravitational sphere of influence, the region where Mars's gravity dominates over the Sun's, allowing the planet to perturb the comet's path measurably. The gravitational interaction operates through invisible geometry, spacetime curved by Mars's mass, creating a gradient that deflects the comet's trajectory without physical contact. The mathematics describing this deflection date to Newton, refined by Einstein but requiring no relativistic corrections at these velocities and masses. Mars's gravity will pull the comet slightly inward as it approaches, accelerating it marginally, then release it on a modified trajectory. The comet's hyperbola slightly rotated, its perihelion distance around the Sun altered by perhaps a few thousand kilometers, negligible compared to the comet's overall path, but measurable with sufficient instrumental precision. The encounter will increase the comet's velocity relative to the Sun by approximately 0.3 kilometers per second, energy extracted from Mars's orbital motion, though the planet's velocity will decrease by an amount so small, measured in micrometers per second, that no instrument could detect the change. Tidal forces act during close approach, differential gravitational pull, attempting to stretch the nucleus along the line connecting its center to Mars's center. The magnitude of these forces depends on the gradient of the gravitational field, stronger at the near side of the nucleus than the far side, creating stress within the ice and rock matrix. For a nucleus 3 kilometers across passing at 44,000 kilometers altitude, tidal stress remains far below the threshold required to fragment the body. Comet Shoemaker-Levy 9 fragmented when passing Jupiter at distances within the Roche limit, where tidal forces exceeded the nucleus's structural strength, tearing it into more than 20 separate pieces that later impacted the planet in sequential spectacular collisions. But Mars, with only 11% of Earth's mass and far smaller than Jupiter, exerts tidal forces insufficient to threaten 3I Atlas's integrity at this passage distance. The nucleus will survive intact, stressed perhaps, but not broken. The trajectory brings the comet across Mars's orbital plane from slightly below, approaching at an inclination of 7 degrees to the ecliptic. This means the comet does not pass directly above Mars in the sense of perpendicular to the planet's orbital motion, but rather sweeps across at an angle, coming from the direction of the planet's trailing hemisphere and departing toward the direction of orbital motion. Observers on Mars's surface were there. Conscious observers would see the comet appear in the western sky shortly after sunset on the approach evening, growing brighter through the night as distance decreases, reaching maximum brightness near dawn when the comet passes closest, then fading rapidly as it recedes. The coma, backlit by the sun during approach, would show full illumination at closest passage, potentially appearing as a diffuse patch rivaling Venus in brightness. Though visibility depends on dust loading in Mars's atmosphere and the observer's location on the planet. No collision hazard exists. The probability calculations, updated daily as new astrometric measurements refine the orbit, consistently yield chances below 1 in 30,000. These probabilities account for uncertainties in the comet's position, velocity, and non-gravitational forces created by outgassing jets that act as weak thrusters, altering the trajectory unpredictably. Cometary orbits cannot be predicted with the same precision as asteroids because sublimation-driven forces vary with rotation, surface composition, and solar heating in ways difficult to model accurately. Despite these uncertainties, the trajectory remains sufficiently well determined that collision can be ruled out with confidence approaching certainty. The solar system is mostly empty space, and even close approaches rarely result in impacts objects pass nearby constantly, deflected into altered paths but seldom intersecting. The passage will occur during Martian northern spring, season defined by the planet's position in its orbit and axial tilt of 25 degrees, similar to Earth's 23-degree tilt, though Mars experiences greater seasonal contrasts due to orbital eccentricity. The northern hemisphere currently warms as increased sunlight melts and sublimates the seasonal carbon dioxide cap, exposing the underlying water ice cap that persists year-round. Atmospheric pressure increases slightly as carbon dioxide returns to the atmosphere from polar reservoirs, a seasonal cycle that causes global pressure variations of about 30%. During closest approach, the comet will pass over Mars's northern mid-latitudes, trajectory aligned roughly northeast to southwest relative to the planet's equator, visible from both hemispheres, though better positioned for southern observers who will see it higher above the horizon. The comet's coma will extend far enough that Mars passes through its outer reaches, not the dense inner coma close to the nucleus, but the tenuous outer envelope where gas and dust densities drop to near interplanetary background levels. Spacecraft in Martian orbit will traverse these regions, instruments potentially detecting increased particle fluxes as the coma's edge sweeps past. The Mars Reconnaissance Orbiter, Mars Odyssey, and several other spacecraft will remain operational during the encounter, their systems deemed unlikely to experience damage from the diffuse material. Cometary dust particles pose some risk to spacecraft impacts at relative velocities of 30 km per second, concentrate enormous kinetic energy into microscopic collisions, but particle density in the outer coma remains low enough that the statistical probability of damaging impacts is acceptably small. Mission controllers accept the minimal risk, recognizing the scientific value of observations during the encounter. Ground-based telescopes on Earth will observe the event, limited by the distance. Mars lies approximately 220 million kilometers from Earth during the encounter, placing the comet at similar distance. Even large telescopes cannot resolve the nucleus at such range, detecting only the integrated light from coma and nucleus combined. Spectroscopy provides the primary scientific return analyzing light to determine composition, gas production rates, and physical conditions in the coma. Multiple observatories coordinate observations to provide continuous coverage, as Earth's rotation carries individual facilities in and out of viewing geometry. Radio telescopes will search for emissions from molecules like ammonia and methanol, tracing the comet's chemistry through characteristic spectral lines. Infrared telescopes will measure thermal emission from dust, constraining particle size distributions and production rates. The encounter geometry creates opportunities for specific observations impossible during most cometary apparitions. As the comet passes Mars, Earth-based observers see it transit across the planet's disk, not a transit in the sense of passing directly between Earth and Mars, but a close conjunction where the comet appears projected near Mars in the sky. Comparing the comet's brightness before, during, and after passing Mars allows scientists to measure how Mars's reflected sunlight illuminates the comet's coma, a photometric experiment providing information about particle size and distribution. The conjunction lasts only hours, requiring coordinated timing and clear weather, constraints that reduce the number of facilities able to participate but increase the value of successful observations. Spacecraft orbiting Mars offer closer views, though none were positioned in orbit specifically for this encounter. Mission planning occurs years in advance, and the comet's arrival was predicted too recently to adjust orbital parameters significantly. Nevertheless, several spacecraft will turn cameras toward the visitor, acquiring images at resolutions far exceeding what Earth-based telescopes can achieve. The Mars Reconnaissance Orbiter carries a high-resolution camera capable of resolving features a few meters across on the Martian surface, pointed at the comet. It might resolve the nucleus itself if distance and viewing geometry cooperate, providing the first direct image of an interstellar object's nucleus. Whether the observations succeed depends on precise timing, orbital position during closest approach, and the unpredictable activity level of the comet's gas and dust production. The encounter will end as abruptly as it began, the comet sweeping past Mars in hours. The gravitational interaction complete, the trajectory modified, but the comet otherwise unchanged. In one sense, nothing will happen. No collision, no catastrophe. Merely two bodies passing in space as occurs countless times throughout the solar system's billions of years. In another sense, everything happens in such passages: gravity exchanging momentum, tidal forces stressing ancient ice, particles transferring from one object to another across the vacuum. The universe operates through such encounters, structure emerging from accumulation of infinitesimal interactions across timescales that dwarf human perception. NASA's Jet Propulsion Laboratory in Pasadena tracks the comet through routine channels established for near-Earth object monitoring. The same systems that catalogue asteroids and assess impact probabilities for objects whose orbits intersect Earth's path. The Minor Planets Centre in Cambridge receives astrometric observations from observatories worldwide, precise measurements of the comet's position against background stars, time-stamped and coordinate-referenced, submitted through standardized formats that allow automated processing. Software ingests these observations, fits orbital parameters through least squares algorithms, generates updated ephemerides predicting future positions, and calculates encounter geometries with planets throughout the inner solar system. The process operates continuously. Updates appearing in online databases accessible to professional astronomers and interested amateurs alike. No restriction on access. No classification of sensitivity. The comet appears in the Near-Earth Object Dynamics site, a public database listing orbital elements, physical characteristics, and close approach data for solar system small bodies. Entry number 3I-2024. C1 contains barycentric orbital elements, reference to the solar system's center of mass. Reducing perturbations from planetary gravity to produce the most accurate trajectory representation, eccentricity equals 1.37, confirming the hyperbolic nature of the orbit. This object arrived from interstellar space and will return there, unbound by solar gravity, a visitor rather than permanent resident. Semi-major axis carries negative value, meaningless for hyperbolic orbits except as mathematical artifact of the equations describing conic sections. Perihelion distance measures 1.42 astronomical units, placing closest solar approach just inside Mars's orbit, explaining the close encounter geometry. Technical bulletins issue from the International Astronomical Union's Central Bureau for Astronomical Telegrams, though telegrams persist only as historical nomenclature for what now distribute as electronic circulars. Circular 10453, published 3 weeks prior, contains spectroscopic observations indicating strong emission from CN, C2, and C3 radicals, daughter species created when organic molecules in the coma fragment under solar ultraviolet radiation. The ratios between these species allow classification of cometary composition types. 3I Atlas shows characteristics intermediate between typical Oort cloud comets and interstellar object 2I Borisov, suggesting formation in an environment chemically similar to but distinct from the Sun's protoplanetary disk. The circular notes gas production rates increasing as expected with decreasing heliocentric distance, observations consistent with models of cometary activity, no anomalous behavior detected. Mars mission operations teams receive briefings on the encounter timeline, not emergency meetings, but scheduled updates during regular planning sessions. The Mars Reconnaissance Orbiter team discusses whether to reorient the spacecraft for observations, weighing scientific value against risk to primary mission operations and fuel expenditure for attitude changes. The Mars Atmosphere and Volatile Evolution Orbiter, designed specifically to study atmospheric escape and solar wind interactions, positions itself to measure potential perturbations as the comet's magnetic field and ion tail sweep past. Engineers calculate worst-case dust flux scenarios, comparing predicted particle densities against spacecraft shielding tolerances concluding that risk remains within acceptable mission parameters. Only took several $billion of spacecraft to warrant such caution. Ground-based radar attempts detection using the Goldstone Deep Space Network antenna in California and the Arecibo successor facility. Though Arecibo's collapse in 2020 removed the most powerful radar telescope from available infrastructure, radar provides direct range measurements and can sometimes resolve nucleus rotation and shape through Doppler, spreading in the returned signal. Initial attempts detect no clear return. The nucleus may be too small, too distant, or too heavily shrouded in coma for radar waves to penetrate and reflect efficiently. Observers will retry as the comet approaches Mars and geometry improves, though success remains uncertain. Radar astronomy operates at the edge of detectability for most targets, successful observations requiring optimal alignment of size, distance, and surface properties. The Hubble Space Telescope allocates 14 orbits, roughly 21 hours of observing time to study the comet before and after Mars encounter. Hubble orbits Earth every 96 minutes, each orbit providing approximately 50 minutes of viewing before Earth occults the target, creating observation windows separated by gaps. The Space Telescope imaging spectrograph will acquire ultraviolet spectra, tracing emissions from hydroxyl radicals that map water production rates. The wide-field camera will image the coma in multiple filters, allowing color analysis that constrains dust properties and composition. These observations compete for time with hundreds of other proposals: distant galaxies, exoplanet atmospheres, stellar phenomena scheduled through a peer review process that ranks scientific merit against available observing hours. The comet earned time through novelty in geometry, its interstellar origin and Mars encounter offering opportunities unavailable for more typical comets. Amateur astronomers contribute observations through networks like the Comet Observation Database, submitting brightness estimates, photographs, and drawings that supplement professional data. Many amateurs possess telescopes and cameras sufficient to detect the comet, track its motion, and measure approximate brightness, creating datasets with broader temporal coverage than professional facilities can maintain, while individual amateur observations carry larger uncertainties than professional measurements. Statistical aggregation of many observations provides valuable information about outbursts, brightness variations, and activity changes that might occur between scheduled professional observing sessions. The division between amateur and professional blurs in modern astronomy. Many amateurs possess sophisticated equipment and training. Some professionals rely on amateur networks to alert them to transient events requiring immediate attention. No press releases announce the encounter with dramatic language or urgent tone. NASA's Public Communications Office prepares a brief article for the website, describing the comet's interstellar origin and Mars flyby in accessible language, noting the scientific observations planned, emphasizing that no danger exists to Martian spacecraft or future human missions. The article appears among other routine updates about planetary missions, telescope discoveries, and administrative announcements, receiving modest attention from science journalists but generating no sustained media coverage. In an era when news cycles demand novelty and immediacy, a comet passing Mars without collision or catastrophe fails to meet thresholds for widespread reporting. The encounter is real, scientifically valuable, and historically noteworthy, the closest approach of a confirmed interstellar object to any planet in the solar system. Yet it occurs quietly, observed by specialists and enthusiasts while broader public attention focuses elsewhere. Social media carries scattered discussion among astronomy communities, Reddit threads analyzing orbital parameters, Twitter posts sharing amateur photographs, YouTube videos explaining encounter geometry with animated diagrams. Conspiracy theorists note the lack of dramatic NASA announcements and construct narratives around perceived silence, interpreting routine scientific process as evidence of concealment. These narratives follow familiar patterns: claims that the comet is actually a spacecraft, assertions that NASA knows something dangerous and refuses to share, speculation about government preparation for impact or alien contact. Such theories reflect misunderstanding of how scientific institutions operate, The absence of alarm is not suppression, but simply reflects the reality that the encounter poses no threat and requires no emergency response. The scientific community continues observations, publishes findings, and shares data through established channels, work proceeding normally while speculation circulates in spaces where evidence matters less than narrative. The silence, to the extent it exists, is not secretive but professional scientists focused on data collection and analysis rather than public spectacle, communicating through technical papers and conference presentations rather than press conferences and dramatic statements. This mode of operation frustrates those who expect science to perform entertainment, to generate excitement and wonder on demand, to translate every observation into implications for human destiny. But cometary astronomy proceeds through patient accumulation of measurements, careful analysis of spectra and images, construction of models that gradually improve accuracy as more data accumulates. The Mars encounter represents one data point among thousands collected over decades of cometary research, valuable for its uniqueness but not revolutionary, adding to knowledge without overturning existing frameworks. The comet appears in observation schedules as target designation 3IR Atlas. Coordinates updated daily, priority rated moderate to high depending on facility and scientific objectives. Telescopes point. Cameras integrate light. Spectrographs disperse wavelengths. Computers store data in formats standardized across decades of astronomical practice. Observers note photometric measurements, record seeing conditions that affect data quality, flag observations contaminated by satellite trails or cosmic ray hits. The work is meticulous, sometimes tedious, requiring attention to instrumental details and environmental factors that can introduce errors. Yet this work, repeated across observatories and nights and targets, constitutes the actual practice of science. Not dramatic discoveries announced in headlines, but careful measurement building toward understanding. Mars and the comet continue their mutual approach. Velocity vectors converging, distance decreasing according to Newtonian prediction, the encounter proceeding as calculated months earlier when orbital elements first achieved sufficient precision to recognize the geometry. In 2 weeks, the comet will sweep past the planet. Instruments will record data, and scientists will begin analysis that may continue for years as subtleties in the measurements reveal information not immediately apparent. The encounter happens once. The understanding unfolds slowly. Knowledge emerging not from single observations but from synthesis of many perspectives, many instruments, many minds considering the same event from different angles. Only took 4 billion years for a solar system to produce observers capable of such synthesis. Mars remembers nothing, yet its surface records everything. 4 billion years of impacts written in craters, valleys carved by ancient water testifying to warmer climates, volcanic plains documenting internal heat budget through geological epochs. Among these records, cometary impacts constitute a significant fraction of the planet's history, though disentangling cometary from asteroidal impacts remains difficult without sample analysis. Comets delivered water to the inner planets during and after formation, augmenting whatever volatiles condensed from the protoplanetary disk's inner regions where temperatures ran too high for water ice stability. Models suggest Earth received 1 to 10% of its ocean mass from cometary impacts, the remainder from water-bearing asteroids and minerals in accreting planetesimals. Mars, smaller and farther from the Sun, may have received proportionally more cometary water, though its weaker gravity also allowed more atmospheric escape once impacts ceased to replenish losses. The late heavy bombardment subjected Mars to intense cometary and asteroidal impacts between 4.1 and 3.8 billion years ago, an epoch when gravitational resonances in the outer solar system destabilized debris populations and scattered them inward. Impact rates during this period exceeded current background rates by factors of thousands, craters forming so rapidly that new impact obliterated evidence of older ones, surface turnover measured in millions rather than billions of years. Large impacts vaporized cometary ice instantly, creating transient atmospheres of steam that precipitated as rain or snow, pooling in impact basins and low-lying areas. Smaller impacts delivered water directly to regolith, the ice sublimating more slowly or reacting with minerals to form hydrated compounds that persist in the subsurface even under current cold-dry conditions. Organic molecules arrived with cometary nuclei complex carbon chains synthesized in interstellar space, or created through radiation chemistry and cometary ice. Upon impact, some organics vaporized or decomposed from shock heating, but material in the outer layers of fragmenting nuclei experienced less extreme temperatures and could survive delivery to the surface relatively intact. These molecules, scattered across Mars's regolith, provided raw materials for prebiotic chemistry if liquid water persisted long enough to allow molecular interactions. Whether such chemistry ever advanced toward life remains unknown. No biosignatures have been definitively detected, though ambiguous results from various missions leave the question unresolved. The Viking landers in the 1970s conducted experiments designed to detect microbial metabolism, returning puzzling results that most scientists interpret as abiotic chemistry, but a few still argue might indicate biological processes. Amino acids, the building blocks of proteins, appear in cometary samples returned from Comet Wild 2 by the Stardust mission, glycine confirmed along with several other simple amino acids. These molecules form readily in cometary ice through ultraviolet irradiation of simpler precursors like water, ammonia, and carbon dioxide. Impact delivery of amino acids to early Mars provided one of many potential sources for these compounds, supplementing whatever formed locally through lightning, ultraviolet radiation, or hydrothermal chemistry. Whether amino acids polymerized into peptides and proteins requires liquid water, concentration mechanisms, and protection from degradation conditions that may or may not have existed on early Mars depending on atmospheric pressure, temperature, and availability of protected environments like hydrothermal springs or subsurface aquifers. Nucleobases, components of DNA and RNA, also appear in carbonaceous chondrite meteorites and likely existed in cometary material, though analysis of returned cometary samples has not yet confirmed their presence directly. Laboratory experiments demonstrate that nucleobases form when water ice containing ammonia, methanol, and other simple molecules is exposed to ultraviolet radiation under conditions resembling interstellar space or cometary surfaces. The same experiments show that these molecules degrade rapidly in the presence of liquid water, unless protected by minerals or concentrated through evaporation. Early Mars, with its uncertain hydrology and unknown chemistry, might have provided conditions suitable for nucleobase survival and incorporation into more complex information-carrying molecules, or might have destroyed them faster than delivery could replenish supplies. The balance between delivery and destruction remains unquantified. Cometary impacts also delivered nitrogen, essential for amino acids and nucleobases, but scarce on Mars's surface today. Atmospheric nitrogen persists as roughly 2.7% of the thin air, but this represents a tiny fraction of the inventory Mars likely possessed early in its history. Nitrogen escapes to space through several mechanisms: solar wind stripping of ionized nitrogen from the upper atmosphere, photochemical reactions that convert nitrogen molecules into atoms with sufficient energy to exceed escape velocity, and impact erosion where large collisions eject atmospheric gases into space. Comets, with their ammonia ice, delivered nitrogen in forms that could be incorporated into atmospheric reservoirs or surface minerals. Over billions of years, as atmospheric loss proceeded, Mars's nitrogen inventory declined to present trace levels, limiting the planet's capacity to support biological chemistry, even if water and organic molecules remained available. Methane detections on Mars, sporadic and controversial, may relate to cometary contributions buried in the subsurface. Methane appears occasionally in atmospheric measurements. Curiosity rover detected spikes of methane concentration in Gale Crater. Orbiting spacecraft measured plumes in specific regions, but global surveys find methane at or below detection limits most of the time. Methane sources remain debated. Geological processes like serpentinization of olivine in the presence of water can produce methane abiotically. Microbial metabolism produces methane on Earth, and cometary impacts throughout history delivered methane frozen in ice. If ancient cometary material remains buried beneath regolith, protected from sublimation by overlying layers, gradual diffusion might release small amounts of methane episodically, explaining sporadic detections. Alternatively, recent micrometeorite impacts might deliver trace amounts continuously, maintaining low background levels. Water ice persists in Martian soil at high latitudes and in permanently shadowed craters near the poles reservoirs, totaling perhaps enough to cover the planet in a global ocean tens of meters deep, if melted and spread evenly. Much of this water arrived via comets during the first billion years, augmented by volcanic outgassing and possibly by water bound in minerals during planet formation. Isotopic measurements of Martian water show deuterium enrichment relative to Earth's oceans. The deuterium to hydrogen ratio is approximately 5 times higher on Mars, indicating preferential loss of lighter hydrogen to space over geological time. This enrichment allows calculation of how much water Mars has lost. Estimates suggest the planet once held enough water to form an ocean covering the northern lowlands to depths of hundreds of meters. Though whether that water ever pooled as a stable ocean or remained frozen most of the time remains uncertain. The northern lowlands show features interpreted as ancient shorelines, terraces and ridges at constant elevation, suggesting water levels that mark the boundary between ocean and land. Dating these features proves difficult without sample return, but crater counting on nearby surfaces suggests ages around 3.5 billion years, consistent with an Oakian or early Hesperian ocean that existed during Mars's wetter epoch. If such an ocean existed, comets contributed significantly to its volume, each impact adding megatons of water that vaporized from impact energy, precipitated as rain or snow, and eventually accumulated in the lowest regions. The ocean, if real, was cold surface temperatures likely near freezing, ice cover possible or probable, circulation driven by what little solar heating penetrated the ice. Such an ocean would have provided immense volumes of liquid water in contact with mineral surfaces, creating environments where chemistry could explore pathways toward complexity. Yet no ocean exists now. Mars lost its water to space and subsurface ice. The atmosphere thinned until liquid water became unstable, and surface temperatures dropped to averages far below freezing. The transformation from wet to dry unfolded over hundreds of millions of years, not catastrophic collapse but gradual decline as atmospheric escape outpaced volcanic replenishment. As the magnetic field died and solar wind began directly stripping ions, as the planet's internal heat decreased and volcanic activity waned, comets continued arriving throughout this transition, each impact delivering water that briefly pooled or soaked into regolith before freezing or sublimating, contributions too small to reverse the trend toward desiccation. Mars became the desert observed today not through single catastrophe, but through accumulation of losses, water molecule by water molecule escaping to space or hiding underground beyond the reach of surface processes. The question of Martian life intertwines with cometary delivery. Did comets provide essential ingredients at the right time and place for life to emerge? Current evidence permits no definitive answer. Mars had liquid water, organic molecules, and energy sources during the same epoch when life arose on Earth. Whether these conditions sufficed for abiogenesis, whether Martian life ever began and subsequently vanished, or whether the planet remained eternally sterile despite apparently favourable conditions, remains one of planetary science's central mysteries. Comets contributed to creating whatever conditions existed, their impacts punctuating Martian history with deliveries of water and organics, their role essential yet insufficient alone to determine the outcome. Only took billions of impacts to pose one unanswered question. The comet crosses one astronomical unit from the Sun-Earth's orbital distance, a threshold where solar radiation intensity equals the value that sustains terrestrial life. drives photosynthesis, maintains liquid oceans. At this distance, sublimation accelerates markedly, the nucleus now receiving solar energy at rates sufficient to vaporize ice, several centimeters deep per day from directly illuminated surfaces. The blackened crust, warmed to temperatures approaching 200 Kelvin in sunlight, conducts heat inward through ice that has remained near absolute zero for billions of years. Temperature gradients create thermal stress expansion at the surface, while deeper layers remain cold and contracted. Stresses that can fracture the crust and open pathways for gas to escape from subsurface reservoirs. Gas production increases to approximately 500 kilograms per second of water vapor, along with proportional amounts of carbon dioxide, carbon monoxide, and trace species. This represents mass loss of roughly 40 tons per hour, 2,000 tons per day, 700,000 tons over the year the comet spends in the inner solar system. For a nucleus containing perhaps 50 billion tons of material, such loss barely registers 1.4% of total mass, enough to thin the surface but insufficient to significantly shrink the nucleus. The sublimation is not uniform but concentrated in active regions where the crust is thin or absent, where fractures expose fresh ice, where rotation brings surfaces into optimal orientation relative to sunlight. Perhaps 5 to 10% of the nucleus's surface actively sublimates at any moment, the remainder insulated by thick dust mantles that trap heat and slow ice loss. Water molecules, freed from the solid matrix, expand into the near vacuum of space at velocities approaching 0.5 kilometer per second thermal velocities determined by temperature and molecular mass. These molecules travel outward from the nucleus, some escaping entirely, others following ballistic trajectories that eventually return them to the surface at different locations, redistributing material from equatorial regions toward poles or from sunlit to shadowed areas. As water molecules move through the expanding coma, solar ultraviolet photons strike them, breaking chemical bonds in photodissociation reactions. Ultraviolet wavelengths shorter than 200 nanometers carry sufficient energy to dissociate water into hydrogen and hydroxyl radical H2O, becoming H and OH, daughter products that themselves absorb and emit light at characteristic wavelengths. Hydroxyl radicals dominate the comet's ultraviolet spectrum. The OH molecule emits strongly at 308 nanometers, creating a glow visible to ultraviolet telescopes as a vast cloud surrounding the nucleus. This hydroxyl coma can extend millions of kilometers, far beyond the visible dust coma, creating the largest observable structure associated with the comet. The OH molecules survive for approximately 1 day before photodissociation breaks them into oxygen and hydrogen, though by then they have travelled far from the nucleus, carried by their initial outward velocity and subsequent photon interactions. Oxygen atoms continue moving outward, occasionally emitting greenish light at 558 nanometers. When excited by solar radiation, this emission gives some comets a faint green colour in telescopic images, though the colour is subtle and often overwhelmed by reflected sunlight from dust. Hydrogen atoms, lightest and fastest, form an even larger cloud around the comet. The hydrogen coma can extend tens of millions of kilometers, becoming the comet's most extensive feature, though invisible to human eyes. Hydrogen emits Lyman alpha radiation at 121 nanometers, detectable only from space-based ultraviolet telescopes, since Earth's atmosphere absorbs these wavelengths. The hydrogen cloud represents water being destroyed, the comet losing its primary volatile in a process that cannot be reversed. Hydrogen escaping the sun's gravitational influence entirely given sufficient velocity. Some comets produce hydrogen clouds large enough to engulf entire planetary orbits, though 3I Atlas, modest in size and activity, creates a hydrogen envelope measuring perhaps 20 million kilometers across, large enough to contain Earth and Moon with room to spare, yet composed of material so diffuse that the total mass equals only a few tons. Carbon dioxide sublimating from the nucleus undergoes its own photochemistry. ultraviolet photons break CO2 into carbon monoxide and atomic oxygen, both of which produce observable emissions. Carbon monoxide appears as a strong emission feature in infrared spectra near 4.7 micrometers, allowing measurement of CO production rates independently of water. The ratio between carbon dioxide and water production varies among comets, reflecting differences in formation conditions and thermal history. Comet 3I Atlas shows CO2-H2O ratio around 10% by number, typical for Oort cloud comets formed at temperatures allowing both species to condense, but with water ice more abundant due to oxygen's greater cosmic abundance and water's efficient formation pathways in interstellar chemistry. Dust grains accelerated by escaping gas begin their separate journey through the coma, larger grains moving more slowly, smaller grains approaching gas velocities, the size distribution determining how quickly dust disperses from the nucleus. Grains smaller than 1 micrometer, comparable to visible light wavelengths, scatter sunlight efficiently, creating the visible coma that extends hundreds of thousands of kilometers from the nucleus. Larger grains, while less efficient at scattering, contribute significant mass to the dust tail that develops as radiation pressure and solar wind gradually accelerate particles away from the sun. The dust tail curves gently, following the comet's orbital path, grains spreading along a fan that marks the trajectory taken as each particle was released. Observing the dust tail's shape allows reconstruction of the comet's mass loss history. Regions of enhanced brightness indicate periods of increased activity. Gaps or filaments reveal rotating jets or discrete outbursts. The comet now sports two tails, the ion tail pointing directly away from the sun, composed of ionized gas molecules accelerated by electromagnetic interactions with the solar wind, and the dust tail curving backward along the orbit, composed of solid particles pushed by radiation pressure. Both tails extend millions of kilometers but contain remarkably little mass. The ion tail might total a few hundred kilograms, the dust tail perhaps thousands of kilograms. Yet these tenuous structures span distances larger than planetary orbits. The disconnection between visual impressiveness and actual mass represents one of cometary astronomy's quiet ironies. Objects appearing substantial in images consist mostly of emptiness, their glow generated by scattering and emission from particles so sparse that the entire tail could be compressed into a volume smaller than a terrestrial building. Solar wind ions flowing past the comet create a bow shock upstream, a boundary where supersonic wind decelerates and compresses as it encounters increased particle density in the cometary coma. This shock, analogous to the bow wave created by a ship moving through water, forms at distances roughly 10,000 to 100,000 kilometers from the nucleus, depending on gas production rate and solar wind conditions. Magnetic field lines carried by the solar wind drape around the coma, the field becoming tangled and compressed, storing magnetic energy that occasionally releases in discrete events. Sometimes the draped field lines reconnect. Severing the ion tail entirely, the tail drifts away into interplanetary space as a disconnected plasma structure, while the comet grows a new tail over subsequent hours. Such disconnection events, triggered by changes in solar wind magnetic field direction, demonstrate the dynamic and transient nature of cometary ion tails. Instruments on Earth-based observatories track all these phenomena, photometry, measuring brightness variations as rotation brings different active regions into view. Spectroscopy recording emission lines that reveal composition and physical conditions. Polarimetry, analyzing scattered light to constrain dust properties. Each measurement contributes to models attempting to explain how cometary nuclei evolve, how outgassing responds to solar heating, how material cycles between surface and coma. The models remain imperfect. Comets exhibit behaviors not fully predicted by current theory. Outbursts occurring without obvious triggers, activity patterns changing from orbit to orbit in ways that suggest subsurface structure, and volatile distribution more complex than simple models assume. Each new comet observed adds to the dataset but also reveals new complexity. Understanding advancing through accumulation of observations rather than breakthrough discoveries, Mars hangs ahead. Now only 10 million kilometers distant 3 weeks at current velocity, the comet's coma will reach the planet before the nucleus arrives. Tenuous outer regions sweeping across spacecraft orbits, delivering microscopic samples of interstellar material to a world that has received such deliveries since its formation. The encounter approaches not as crisis but as confluence. Two bodies following paths determined eons ago, briefly intersecting before diverging forever into the vastness that contains them both. Only took the lifetime of the universe to arrange this moment of passage. Phobos completes another orbit, racing across Martian sky 3 times, while the planet rotates once beneath it. The Moon measures 27 by 22 by 18 kilometers, an irregular ellipsoid of rock and regolith. Too small for gravity to pull it into spherical form, its shape determined by accretion processes and whatever collision fragmented the parent body from which it might derive. Its surface, covered in a layer of loose dust estimated between 50 and 100 meters deep, has been gardened by 4 billion years of micrometeorite impacts, each tiny collision vaporizing a portion of surface material, ejecting fragments that mostly escape the Moon's weak gravity, settling the remainder back into slightly different configurations. The dust accumulates endlessly. No atmosphere exists to redistribute it. No geological activity refreshes the surface. Phobos's exterior represents pure impact processing, bombardment the only sculptor. Craters pock the surface, the largest being Stickney, a 9-kilometer impact structure that dominates Phobos's leading hemisphere. The crater so large relative to the Moon that the impact nearly shattered the entire body. Grooves radiate from Stickney across the surface. Parallel trenches tens to hundreds of meters wide and sometimes several kilometers long, their origin debated since discovery. Some researchers interpret the grooves as fractures created by the Stickney impact, stress waves propagating through the Moon's interior and cracking the surface in radial patterns. Others suggest the grooves form as Phobos orbits through Mars's gravity gradient, tidal stress slowly pulling the Moon apart along lines of weakness, the grooves representing incipient fracturing that will eventually fragment Phobos entirely. The grooves may also be chains of small craters, aligned by chance or by secondary ejecta from larger impacts, or they may result from rolling boulders leaving tracks as they migrate downslope under Phobos's feeble gravity. The Moon's orbit lies nearly circular, inclined only 1 degree to Mars's equator, at altitude of only 9,376 kilometers, measured to the meter by laser ranging from spacecraft. The precision absurd given Phobos's irregular shape makes defining a mean radius somewhat arbitrary. This orbit lies well inside synchronous altitude, where a Moon would orbit at the same rate Mars rotates. Synchronous orbit for Mars occurs at 20,000 kilometers. More than twice Phobos's distance. Being inside synchronous altitude means tidal forces slowly steal angular momentum from Phobos's orbit, transferring it to Mars's rotation, gradually lowering Phobos's altitude by approximately 1.8 centimeters per year. This inward spiral dooms Phobos to eventual destruction, either collision with Mars's surface in approximately 30 to 50 million years, or tidal disruption into a ring system when the Moon descends below the Roche limit the distance where Mars's tidal forces exceed Phobos's structural strength. Deimos orbits farther out at 23,460 kilometers above synchronous altitude, which means tidal forces add energy to its orbit rather than removing it. Deimos slowly recedes from Mars, its orbit expanding by approximately 3 centimeters per year. Though at its current distance, tidal effects are weak, and the outward migration will continue for billions of years before carrying Deimos into interplanetary space. The Moon measures 15 by 12 by 11 kilometers, smaller than Phobos, similarly irregular, similarly covered in deep regolith. Its surface appears smoother in imaging, fewer large craters, the dust layer possibly even thicker. Deimos reflects only 6% of incident sunlight, its surface among the darkest in the solar system, comparable to charcoal, suggesting carbonaceous composition similar to primitive asteroids from the outer main belt or beyond. Both moons likely originated as asteroids captured by Mars's gravity. Though capture mechanics remain unclear, asteroids approaching Mars on unbound orbits cannot spontaneously become satellites without losing energy, typically through atmospheric drag, collision, or multibody gravitational interaction. Mars's thin atmosphere would provide minimal drag at the altitudes where Phobos and Deimos orbit, ruling out aerocapture. Collision-based capture would likely fragment the incoming body, possibly explaining why Mars has two moons rather than one, though their similar orbits suggest common origin rather than independent captures. Three-body interactions involving Mars, the Sun, and an asteroid could allow capture if timing and geometry aligned precisely. A low-probability event, but possible over billions of years. Alternative hypotheses propose Phobos and Deimos formed in orbit around Mars from debris created by a large impact, similar to how Earth's moon formed, though Mars's small mass makes such impacts less likely, and subsequent debris dynamics different from the Earth-Moon system. Spectroscopy of Phobos and Deimos shows absorption features matching D-type asteroids, a rare class found predominantly in the outer main belt beyond 3 astronomical units from the Sun. These asteroids, and thus possibly Phobos and Deimos, contain significant amounts of carbon and organic compounds, their dark surfaces resulting from complex hydrocarbons created by radiation processing of carbon-rich minerals. If Phobos and Deimos are captured D-type asteroids, they formed farther from the Sun than Mars orbits, and migrated inward through gravitational interactions. Perhaps during the era of planetary migration, when Jupiter and Saturn's orbits shifted and perturbed countless asteroids into new trajectories. This scenario explains the Moon's composition, but requires explaining how capture occurred despite the dynamical difficulties. The Moons witness every comet that approaches Mars. They have no eyes to see, no sensors to record, no memory to preserve, yet their surfaces accumulate the evidence. Cometary dust settling onto Phobos and Deimos over billions of years mixes into the regolith micrometeoritic bombardment, gradually stirring the upper layers, distributing material through the dust column. Each cometary encounter deposits microscopic amounts nanograms per square meter for distant passages, micrograms for close encounters, occasionally milligrams if the Moon passes directly through a dense region of the coma. These contributions are undetectable individually, but accumulate across geological time, contributing trace amounts of water ice, organic compounds, and volatile elements to the Moon's surfaces. No spacecraft has yet returned samples from Phobos or Deimos. Though missions are planned, Japan's MMX mission aims to collect material from Phobos and return it to Earth in the early 2030s. Potentially answering questions about the Moon's origin and composition that remain unresolved from remote sensing. The samples may contain cometary material, pre-solar grains, organic molecules from interstellar space, all embedded in regolith that records Mars system history. Finding and identifying such inclusions will require careful laboratory analysis, separating indigenous material from later additions, matching isotopic signatures with known cometary compositions. The analysis may take decades, yielding results long after the collection mission returns. Knowledge unfolding slowly as techniques improve, and researchers discover questions they did not know to ask when samples first arrived. Phobos crosses the Martian sky rapidly from the surface perspective, rising in the west, visible for only 4 hours before setting in the east, appearing again 8 hours later for another brief transit. Deimos moves more sedately, rising in the east, taking nearly 3 days to cross from horizon to horizon, appearing as a bright star rather than a disk to hypothetical observers on the surface. Neither moon shows phases as seen from Mars. Phobos always appears full, its orbit lying inside the shadow cone cast by Mars, only occasionally transiting the Sun as a small dark disk rather than passing through eclipse. Deimos, orbiting at greater distance, can experience eclipses when passing into Mars's shadow, cooling rapidly in darkness before emerging back into sunlight. The comet approaches their orbital space trajectory. Calculations show it will pass between the orbits of Phobos and Deimos, threading the narrow gap between 9,000 and 23,000 kilometer altitude. Neither moon will experience close encounter, Minimum distance to Phobos exceeds 40,000 kilometers. To Deimos slightly more, but both will lie within the comet's extended coma, the tenuous outer envelope where particle density drops to interplanetary background levels, yet where instruments might detect enhanced flux of dust and ions. If instruments existed on Phobos or Deimos to make such measurements, instead the moons continue their silent circuits, Phobos racing inward toward eventual destruction, Deimos slowly drifting outward toward ejection, both marking time through orbit and rotation, participating in Mars system dynamics without awareness or intent. The comet will pass them in 3 weeks. The moons will occupy different positions in their orbits when the encounter occurs. Geometry determined by the moon's orbital periods and the comet's arrival time. Phobos completes 3 orbits per Martian day. Deimos requires 30 hours per orbit, their positions relative to each other, and Mars constantly shifting through complex patterns that repeat only over long cycles. When 3i Atlas sweeps past, Phobos might be over the day side or night side, approaching the planet or receding, its position essentially random relative to the comet's trajectory. Deimos similarly occupies some position determined by its orbital mechanics, no special alignment occurring. The encounter geometry driven by solar system dynamics rather than Martian system choreography. The moons will witness the passage to whatever extent a lifeless rock witnesses anything. Photons from the comet will strike their surfaces, some reflected, some absorbed, the interaction leaving no permanent record distinguishable from billions of years of similar illuminations. Only took the formation of a solar system to create such indifferent observers. The probability calculation updates daily as new astrometric measurements refine the comet's position and velocity vectors. Each observation, a precise measurement of right ascension and declination at a specific time, accurate to within fractions of an arc-second, constrains the orbit slightly more, reducing uncertainties in future position predictions. The orbital elements contain error bars, statistical ranges representing the confidence with which each parameter is known. Semi-major axis carries uncertainty of plus or minus 3 astronomical units, meaningless for trajectory prediction, but reflecting the difficulty of determining hyperbolic orbit parameters from limited observation arcs. Eccentricity is known to 4 decimal places 1.3704 plus or minus 0.0003, sufficient precision to confirm the orbit's hyperbolic nature beyond doubt. Perihelion distance. The parameter most relevant for Mars encounter geometry is measured at 1.421 astronomical units, with uncertainty of plus or minus 0.0008 astronomical units, roughly 120,000 kilometers. This uncertainty, while small in absolute terms, spans distances larger than Mars itself, introducing ambiguity into closest approach predictions. The time of perihelion passage is known to within 6 minutes, position along the orbit at any given time, constrained by the accumulated observations but still uncertain enough that impact probability calculations must account for these ranges. Monte Carlo simulations run thousands of virtual comets through orbits sampled from the probability distribution of orbital elements, calculating how many trajectories result in collision with Mars, how many pass at various distances, constructing statistical predictions of encounter outcomes. Current simulations yield collision probability of 0.003%, 3 chances in 100,000, low enough to classify the encounter as safe but not zero. The non-zero probability reflects genuine uncertainty rather than actual danger with perfect knowledge of position and velocity. The probability would collapse to 0 or 100%, the outcome determined. But observations contain measurement errors. The comet experiences non-gravitational forces from outgassing that perturb the trajectory unpredictably, and tracking data spans only months rather than the years or decades that would allow more precise orbit determination. The 3 in 100,000 probability means that if we could observe 100,000 comets with identical orbital uncertainties, roughly 3 would collide with Mars, a statistical statement about confidence. not a physical statement about this specific comet's fate. Non-gravitational forces complicate prediction. Jets of sublimating gas act as tiny rockets, each jet producing thrust when gas escapes preferentially from one side of the nucleus. These jets, tied to rotation and solar heating geometry, create acceleration components that change the comet's velocity by fractions of a millimeter per second, tiny effects, but sufficient to alter position predictions by thousands of kilometers over weeks of travel. The magnitude and direction of non-gravitational forces depend on the nucleus's shape, rotation state, and active area distribution, properties known only approximately for 3I Atlas. Models attempt to account for these forces by including parameters for radial, transverse, and normal acceleration components, fitting these parameters to observed positions along with gravitational orbital elements. The fits improve prediction accuracy, but cannot eliminate uncertainty. Comets sometimes undergo outbursts that suddenly increase gas production, creating impulsive changes in trajectory that no model based on past behavior can anticipate. The comet's activity level appears stable, no major outburst detected. Brightness increasing smoothly as expected, with decreasing heliocentric distance. Spectroscopic signatures consistent with standard cometary chemistry. This stability suggests the non-gravitational forces remain relatively constant, improving confidence in trajectory predictions. If an outburst occurs between now and Mars encounter, the prediction would require updating with new observations made after the outburst, orbital elements refitted, probability calculations rerun. Observers monitor the comet daily for such changes, brightness measurements flagging potential outbursts. Though distinguishing genuine activity changes from observational noise or rotational brightness variations requires careful analysis. Mars presents a small target. The planet's diameter spans 6,780 kilometers, creating a collision cross-section of approximately 36 million square kilometers. Large in terrestrial terms, but tiny compared to the uncertainty envelope surrounding the comet's predicted position at encounter time. The uncertainty region, if visualized, would appear as an elongated ellipsoid stretching millions of kilometers along the comet's trajectory, hundreds of thousands of kilometers across perpendicular to motion a fuzzy cloud of possible positions. Each location within the cloud assigned a probability based on how well it fits the observational data and dynamical models. Mars occupies a tiny portion of this uncertainty cloud, most of the probability distribution lying in empty space far from planetary encounter. Gravitational focusing enhances collision probability. Slightly objects approaching a planet on near-miss trajectories are gravitationally attracted, their paths bent toward the planet, effectively increasing the collision cross-section beyond the planet's physical size. For objects approaching at interstellar velocities, gravitational focusing adds only a few % to the collision probability. Mars's gravity is too weak, and the approach velocity too high for significant deflection. The enhancement factor equals approximately 1 plus the square of escape velocity divided by the square of approach velocity. Mars's escape velocity measures 5 kilometers per second. The comet's approach velocity relative to Mars is roughly 32 kilometers per second, yielding enhancement of about 3%. The calculations account for this effect, folding it into the Monte Carlo simulations that generate overall probability estimates. Atmospheric entry would vaporize the nucleus. A 3-kilometer ice ball striking atmosphere at 32 kilometers per second would release kinetic energy equivalent to roughly 100,000 megatons of TNT, comparable to the largest impact events in Earth's geological record. The energy would convert to heat through atmospheric compression and friction, vaporizing the nucleus in seconds, creating a fireball that would temporarily rival the Sun in brightness as seen from Mars's surface. Atmospheric shock waves would propagate downward and outward, potentially stripping significant fractions of the atmosphere to space, while ejecta from the impact crater would blanket the planet in dust, creating an impact winter lasting years or decades. No spacecraft on the surface or in orbit would survive such an event. The Martian exploration program would end abruptly. along with any hypothetical subsurface microbial ecosystems that might inhabit protected niches. But the 3 in 100,000 probability renders such scenarios academic engineering risks at these probability levels are routinely accepted in spacecraft design, where component failure rates often exceed 1 in 10,000 and mission success requires thousands of components functioning correctly. The probability is higher than being struck by lightning during a given outdoor hour, but lower than experiencing a vehicle accident during a specific trip. Such comparisons provide little intuitive guidance. Humans assess risk poorly at these probability levels. Cognitive biases alternately inflating or dismissing dangers based on availability, emotional resonance, and narrative coherence rather than statistical reality. Mission planners accept the risk as negligible. No changes to spacecraft operations are implemented beyond the already planned observations. No protective measures taken beyond those standard for all cometary passages. The spacecraft, designed to survive the Martian radiation environment and occasional solar particle events, possess shielding adequate for the diffuse dust environment of the comet's outer coma. The probability that any individual spacecraft encounters a dust particle large enough to cause damage is far lower than the already low collision probability, making dust hazard essentially zero in practical terms. Engineers calculate worst-case scenarios out of professional thoroughness, finding that even under pessimistic assumptions about dust density and particle size distribution, risk remains within acceptable mission parameters. Ground-based observers continue tracking, measurements accumulating, uncertainties shrinking each new position. Measurement adds information, orbit determination improving asymptotically toward perfect knowledge, though never quite reaching it. 2 weeks remain until encounter, time for perhaps 30 additional observations from various facilities, enough to reduce position uncertainty at encounter time to perhaps 50,000 kilometers. The probability will likely decrease as the orbit becomes better known. Though surprises remain possible, an outburst could alter the trajectory. A previously undetected systematic error in measurements could be discovered and corrected, or simply the random distribution of a measurement errors could shift the most probable trajectory slightly. The probability might drop to 1 in 10 million or rise to 1 in 10,000, but barring unexpected activity changes, impact remains overwhelmingly unlikely. The comet continues inbound, indifferent to probability calculations, following the path determined by gravity and momentum, its trajectory already fixed by initial conditions and forces acting since departure from its distant formation site. The probability exists in human assessment, not in physical reality. The comet will either hit Mars or miss it. Binary outcome determined by actual position and velocity at encounter time, quantities that exist with precision regardless of measurement uncertainty. Only the observers lack knowledge, calculating probabilities to quantify their ignorance, preparing for an encounter whose outcome is already determined though not yet revealed. Only took 4.5 billion years to create beings capable of such anticipatory anxiety about events they cannot influence. Spectrographs dissect the comet's light into constituent wavelengths, spreading the integrated glow across detector arrays that record intensity at each frequency, with precision measured in parts per thousand. The resulting spectrum appears as a graph wavelength on horizontal axis, flux on vertical, decorated with emission lines rising above the continuum like peaks in a mountain range, each peak corresponding to specific atomic or molecular transitions. The spectrum tells stories about composition, temperature, velocity, excitation state, all encoded in the positions, widths, and intensities of these spectral features. Reading the spectrum requires knowledge of atomic physics, quantum mechanics, and statistical thermodynamics. The lines represent photons emitted when electrons transition between energy levels in atoms and molecules excited by solar radiation or collisions. The hydroxyl radical produces strong emission at 3080 angstroms, ultraviolet wavelength, observable only from space or high-altitude aircraft. Earth's atmosphere absorbing these photons before they reach ground-based telescopes. The emission results from OH molecules created when water photodissociates, absorbing solar ultraviolet light and fluorescing, re-emitting at characteristic wavelengths as excited electrons return to lower energy states. The intensity of hydroxyl emission correlates directly with water production rate, allowing astronomers to calculate how many water molecules escape the nucleus per second. Current observations indicate production of approximately 500 kilograms per second, or about 5 times 10 to the 27th molecules per second. Each molecule eventually destroyed through photodissociation, contributing hydrogen and oxygen atoms to the expanding coma. Cyanogen CN radical composed of carbon and nitrogen emits a strong band near 3,800 angstroms, creating the violet coloration sometimes visible in cometary spectra. CN forms when more complex parent molecules containing carbon-nitrogen bonds undergo photochemical destruction in the coma. The parent molecules remain uncertain. Hydrogen cyanide is likely, along with possibly more complex nitriles, but CN itself is the observable daughter product, its emission allowing measurement of nitrogen-bearing volatile production. The CN to OH ratio varies among comets, reflecting differences in composition related to formation temperature and chemical environment. Comet 3I Atlas shows CN to OH ratio around 0.3%, slightly higher than typical solar system comets, perhaps indicating formation in a molecular cloud with enhanced nitrogen abundance or different chemical pathways than those operating in the Sun's protoplanetary disk. Diatomic carbon C2 emits green light near 5,100 angstroms, a wavelength easily observed from ground-based telescopes and contributing to the greenish tint some comets display. C2 forms through complex photochemistry involving carbon-bearing molecules, possibly from fragmentation of larger organic species in the nucleus or from recombination of atomic carbon in the coma. The production mechanism remains incompletely understood, though laboratory experiments and theoretical models have narrowed the possibilities. The C2 emission intensity relative to other species provides diagnostic information about the comet's organic inventory, particularly the abundance of complex hydrocarbons that might serve as parent molecules. Sodium emission appears as 2 bright lines, the sodium D lines at 5,890 and 5,896 angstroms, when dust grains in the coma are sputtered by solar ultraviolet radiation. Sodium atoms released from silicate minerals fluoresce strongly, creating an extended sodium tail that can stretch millions of kilometers. The sodium emission is sporadic, varying with dust production and possibly with the composition of ejected material. Some regions of the nucleus may contain more sodium-rich minerals than others, creating brightness variations as rotation brings different areas into sunlight. Current observations show weak sodium emission from 3I Atlas, suggesting either low dust production rates or dust composition dominated by carbon-rich material rather than silicates. Isotopic ratios hide in the fine details of spectral lines. Molecules containing different isotopes emit at slightly different wavelengths due to mass differences affecting vibrational and rotational energy levels. Deuterated water, HDO, instead of H2O emits at wavelengths shifted by small amounts from regular water, the shift proportional to the mass ratio between hydrogen and deuterium. Measuring the HDO to H2O ratio requires high spectral resolution and sensitivity, observations typically possible only with specialized instruments on large telescopes or space-based observatories. Early observations of 3I Atlas suggest deuterium enrichment compared to terrestrial water. The D to H ratio appears approximately twice Earth's ocean value. Though uncertainties remain large and additional observations are needed for confirmation, this deuterium ratio carries information about formation temperature. Deuterium, enrichment in water, ice increases at lower temperatures. The heavier isotope preferentially incorporating into solid phase over gas phase through quantum mechanical effects that favor formation of stronger bonds with heavier atoms. The ratio measured in 3I Atlas, if confirmed, suggests formation at temperatures near 30 Kelvin, consistent with condensation in cold molecular clouds or the outer regions of protoplanetary disks beyond the ice line. Comparing this ratio with values measured in solar system comets helps constrain where 3I Atlas formed relative to its parent star, and whether that formation environment differed significantly from the Sun's protoplanetary disk. Presolar grains, dust particles that formed around other stars before being incorporated into the comet, cannot be identified spectroscopically in the coma. These grains, composed of silicon carbide, graphite, diamonds, and various oxides, are too small and too mixed with indigenous dust to show diagnostic spectral features at cometary distances. Only by collecting samples and analysing individual grains in laboratory mass spectrometers can pre-solar materials be identified and characterised. Stardust mission samples from Comet Wild 2 contained pre-solar grains, though they composed less than 1% of total dust mass rare inclusions, carrying isotopic signatures from red giant stars, supernovae, and other stellar sources. Comet 3I Atlas presumably contains similar pre-solar components, formed in stars that died before the Sun ignited, now travelling through another stellar system after billions of years in interstellar space. Organic molecules detected in the spectrum include formaldehyde, methanol, ethane, and possibly more complex species whose identification requires infrared spectroscopy at wavelengths, where molecular vibrational transitions create characteristic absorption and emission features. These organics, created through radiation chemistry in icy grain mantles, or perhaps synthesized in the comet's formation environment, represent some of the most complex chemistry occurring in space. Methanol CH3OH forms efficiently on cold grain surfaces where hydrogen atoms added sequentially to frozen carbon monoxide build up molecular complexity. Formaldehyde H2CO forms similarly, though requiring fewer hydrogen additions. Both molecules appear common in comets, dense molecular clouds, and star-forming regions, suggesting robust formation pathways that operate across diverse environments. The spectrum also reveals what is absent: no evidence of molecular nitrogen, despite nitrogen being the fourth most abundant element cosmically. Molecular nitrogen N2 lacks permanent dipole moment, and therefore produces no rotational or vibrational transitions in wavelength ranges accessible to spectroscopy. Its presence can be inferred indirectly from measurements of nitrogen-bearing daughter products like CN, or from mass spectrometry during spacecraft flybys. But remote spectroscopy remains blind to this potentially major volatile. Some models suggest comets contain significant nitrogen as N2 ice, comparable in abundance to carbon monoxide, but observational confirmation is lacking. The nitrogen budget of comets remains uncertain, complicating models of how much nitrogen comets delivered to early planets and how that nitrogen partitioned between atmosphere and surface. Forbidden lines, transitions that violate selection rules in normal conditions but become allowed in the low-density coma, where collisions are rare, appear in cometary spectra as weak features. Atomic oxygen emits green and red forbidden lines at wavelengths used by astronomers to study planetary nebulae and diffuse nebulae. In comets, these lines trace oxygen atoms produced by water and carbon dioxide photodissociation, providing complementary information to the allowed transitions observed at other wavelengths. The forbidden line intensities depend on electron density and temperature in the coma, allowing derivation of physical conditions from spectral measurements. The spectral data accumulates in archives FITS files containing flux measurements at thousands of wavelengths, metadata recording observation times and conditions, calibration files allowing conversion from instrumental units to physical fluxes. Astronomers worldwide access these archives, extracting spectra for analysis, comparing measurements across different facilities, searching for temporal variations that might indicate changing activity. Papers appear in journals months or years after observations, reporting production rates, composition ratios, isotopic measurements, each paper adding incremental knowledge to cometary science. The comet itself continues toward Mars, indifferent to the analysis. Its chemistry, determined billions of years ago, now revealed through light travelling across the solar system to be captured, dispersed, and interpreted, only took the evolution of observers capable of quantum mechanics to decode messages written in wavelength and intensity. Mars once held water pooled in basins where terrain descended below datum, the reference elevation defined by mean atmospheric pressure and gravitational equipotential surface, though defining such surfaces on a planet without oceans remains somewhat arbitrary. The northern lowlands, lying 4 to 5 kilometers below the southern highlands, represented the deepest accessible regions, natural collecting areas for any liquid water existing at the surface. Models suggest that during the Noachian period, roughly 4 billion years ago, atmospheric pressure may have reached values sufficient to stabilize liquid water, perhaps several hundred millibars, 10 to 20% of Earth's current sea level pressure, enough to prevent immediate boiling but creating an environment far more hostile than any terrestrial ocean. That ancient atmosphere, if it existed at such density, consisted primarily of carbon dioxide with significant water vapor, possibly some nitrogen, trace amounts of other gases released by volcanic outgassing or delivered by impacting comets. The greenhouse effect from carbon dioxide would have warmed the surface slightly. Though solar luminosity at that epoch was only 70 to 75% of current values, the faint young sun problem that complicates all models of early planetary climates, even with substantial greenhouse warming, mean temperatures likely hovered near freezing. Any liquid water existing in narrow temperature ranges maintained by geothermal heat, transient volcanic warming, or impact-generated thermal pulses. The ocean, if it existed, was never tropical cold, possibly covered by ice much of the time, more similar to Earth's polar seas than to temperate or equatorial waters. Valley networks carved into ancient terrain suggest water flowed episodically at the surface, though whether fed by rainfall, snowmelt, or groundwater sapping remains debated. The valleys show branching patterns similar to terrestrial rivers, tributaries joining to form larger channels that drained toward the northern lowlands. Dating the valleys proves difficult. Crater counting on adjacent terrain suggests formation mostly during the Noachian and early Hesperian periods, between 4 and 3.5 billion years ago, though some valleys may have remained active longer or experienced multiple episodes of flow separated by long dormant intervals. The valleys are now dry, filled with dust, their channels unmodified except by wind and occasional slope failures. Last flow occurring billions of years before primates evolved on Earth. Hydrated minerals detected from orbit provide evidence of extended water-rock interaction clays, sulfates, carbonates, indicating water persisted long enough to weather rock and deposit secondary minerals in layers now exposed by erosion. Clay minerals form when water with near-neutral pH interacts with volcanic rock, dissolving primary minerals and precipitating new phases stable under aqueous conditions. The process requires liquid water in contact with rock for thousands to millions of years, timescale suggesting not merely transient flows but sustained presence of water, whether as groundwater permeating porous rock or as surface pools in basins and impact craters. The clays exist predominantly in Noachian terrain, supporting the hypothesis that early Mars was wetter than later epochs. Sulfate deposits appear in younger terrain, Hesperian and Amazonian age surfaces suggesting environmental transition from neutral to acidic conditions as volcanic sulfur dioxide reacted with water to form sulfuric acid. Sulfates precipitate when acidic water evaporates or when pH changes bring the solution to saturation, forming layers sometimes hundreds of meters thick as documented by orbital spectroscopy and in situ rover measurements. The transition from clay to sulfate mineralogy records Mars drying out, an atmospheric composition shifting toward more acidic conditions, possibly as volcanic activity waned and water became scarce, allowing sulfur compounds to concentrate without dilution. Carbonate minerals, expected to form abundantly on a planet with thick carbon dioxide atmosphere and liquid water, appear only in trace amounts, a puzzle suggesting either that Mars's ancient atmosphere was not as dense or CO2 rich as some models propose, or that conditions prevented carbonate precipitation despite available constituents. Terrestrial oceans precipitate vast quantities of calcium carbonate as organisms build shells and skeletons. But abiotic carbonate formation requires alkaline conditions and sufficient calcium dissolved in water. If Martian waters were acidic or calcium poor, carbonate formation would be suppressed. Alternatively, carbonates may have formed and subsequently dissolved or metamorphosed, removing them from the geological record except in protected niches. The water that filled ancient basins and flowed through valleys no longer exists in liquid form. Most escaped to space as hydrogen after photodissociation broke water molecules apart. Solar ultraviolet radiation penetrating the upper atmosphere splits water vapor into hydrogen and oxygen, the hydrogen being light enough to escape Mars's gravity given sufficient thermal velocity. The process operates continuously, currently stripping approximately 100 grams of hydrogen per second from Mars's upper atmosphere, equivalent to losing several thousand tons of water annually, over 4 billion years, at rates that may have been higher when solar ultraviolet flux was stronger and Mars's atmosphere thicker. This process removed ocean-scale quantities of water molecule by molecule. Oxygen from photodissociated water largely remained on Mars, too heavy to escape as efficiently as hydrogen. Most oxygen reacted with iron-bearing minerals at the surface, oxidizing ferrous iron to ferric iron and creating the iron oxides that color the soil rust red. The oxidation process consumed oxygen over billions of years, the planet's surface acting as a giant chemical sponge absorbing oxygen atoms freed from water molecules. Some oxygen escaped to space. Current measurements show oxygen loss rates around 10 times higher than hydrogen by mass, though far less than stoichiometric ratios from water dissociation would produce, confirming that most oxygen remains trapped in surface chemistry. The magnetic field's collapse approximately 4 billion years ago accelerated atmospheric loss by exposing the upper atmosphere directly to solar wind. Earth's magnetic field deflects solar wind around the planet, creating a protective magnetosphere that shields atmosphere from direct stripping. Mars, lacking global magnetic field, experiences solar wind penetrating to ionospheric altitudes, where it ionizes atmospheric gases and sweeps ions away through electromagnetic coupling. The process is inefficient. Most atmosphere remains gravitationally bound but operating over billions of years. It eroded the thick early atmosphere to present trace levels. Mars, atmosphere and volatile evolution orbiter measurements show current atmospheric loss rates of approximately 100 grams per second, dominated by oxygen and carbon dioxide ions, with hydrogen escaping mainly through thermal processes rather than ion pickup. Comets contributed to the ancient ocean. Each impact delivered water that vaporized from collision energy, entered the atmosphere as steam, condensed as rain or snow when temperatures allowed, and eventually accumulated in low-lying areas. The total cometary contribution remains uncertain. Estimates range from 10 to 50% of Mars's initial water inventory, the remainder coming from volcanic outgassing, asteroids, or water incorporated into planetesimals during Mars's formation. Distinguishing between these sources requires isotopic measurements, comparing Martian water to cometary ice, asteroidal minerals, and volcanic gases measurements possible only with returned samples, or in situ analysis beyond current mission capabilities. The ocean's existence remains hypothetical features interpreted as shorelines could alternatively be explained by wind erosion, lava flow boundaries, or glacial processes without requiring standing body of water. Some researchers argue the evidence for ancient ocean is strong. Others remain skeptical, the debate unresolved pending additional data. If the ocean existed, it was not permanent. Geological evidence suggests any large water bodies were transient on timescales of millions to tens of millions of years, existing during favorable climate intervals when volcanic outgassing temporarily thickened the atmosphere, or orbital variations increased solar heating. Between wet episodes, the water froze into ice sheets or soaked into porous regolith, hiding underground beyond the reach of sublimation and atmospheric loss processes. Life, if it arose on Mars, would have exploited these wet intervals using liquid water for biochemistry, extracting energy from chemical gradients between reduced and oxidized minerals. Reproducing before water froze or evaporated, terrestrial life colonizes every environment where liquid water persists, from Antarctic ice to deep subsurface rock, demonstrating that life requires surprisingly little beyond water and energy. Mars offered both during the Noachian, though whether the conditions sufficed for a biogenesis or whether life appeared only to vanish when habitability declined remains unknown. Current missions search for biosignatures in ancient rocks, chemical or morphological evidence that would indicate past biological activity, so far without definitive results. The comet approaching Mars now carries water similar to that which filled ancient basins, isotopically different, formed in another stellar system, but chemically identical. H2O molecules indifferent to origin, capable of the same chemistry regardless of whether they condensed around the Sun or another star. If the comet's ice could be harvested, melted, purified, it would create water indistinguishable from terrestrial oceans or Martian polar caps, suitable for any use water serves. The comet contains enough ice to fill a terrestrial lake several kilometers across and hundreds of meters deep, volumes that seem substantial until compared with the ocean. Mars lost the comet could impact Mars and vaporize completely, adding its water to atmosphere and surface, contributing less than 1/1,000,000,000th of what the planet lost over geological time. Only took billions of years to transform an ocean into a desert one molecule at a time. The silence surrounding 3i Atlas reflects standard practice in planetary astronomy, routine observations catalogued through established channels, data published in technical journals and online databases, information accessible to anyone with internet connection and interest in orbital mechanics. NASA's Near-Earth Object Program maintains public websites listing all tracked objects, their orbital parameters updated as new observations arrive, close approach predictions computed automatically and displayed without editorial commentary. The comet appears in these listings with designation, discovery date, orbital elements, physical characteristics estimated from brightness and spectroscopy, and encounter predictions for Mars, Earth, and other solar system bodies. No information is classified, no data withheld, no secret briefings conducted. The absence of dramatic announcement stems from absence of drama rather than suppression of dangerous knowledge. Media coverage of space events follows patterns established over decades. Missions to other planets generate interest. Landings on Mars or flybys of outer solar system bodies attract attention. Telescopic discoveries of distant galaxies or exoplanets earn headlines if framed properly. Comets receive coverage when visible to naked eye or when projected to become spectacular. Comet Neowise in 2020 generated substantial interest because observers at northern latitudes could see it without optical aid. Evening sky adorned with visible tail for weeks during summer. Comet 3i Atlas, at 10th magnitude even near peak brightness, requires telescope for observation, removing it from public consciousness despite scientific significance. The close approach to Mars interests specialists but lacks narrative elements that generate broad engagement. No collision threat, no spectacular display, no human drama to anchor the story. Conspiracy theories fill perceived information voids, interpreting silence as evidence of concealment when silence actually indicates normalcy. The reasoning follows familiar patterns. Large astronomical event occurs. Official sources do not declare emergency. Therefore, authorities must be hiding something. The logic fails through misunderstanding how scientific institutions operate. Astronomers observe, measure, analyze, publish, the process proceeding through peer review and conferences rather than press releases and public alarms. Events warranting immediate public notification follow protocols established for planetary defense if an object posed significant impact threat to Earth. Coordinated announcements would emerge from NASA's Planetary Defense Coordination Office, European Space Agency's NEO Coordination Center, and other agencies through channels established specifically for such notifications. The probability that NASA would successfully conceal imminent cometary impact on Mars approaches zero given the distributed nature of astronomical observation. Amateur astronomers worldwide track comets. Professional observatories in dozens of countries independently measure positions and orbits. International coordination through the Minor Planets Center and International Astronomical Union ensures data sharing across national boundaries. No single agency controls information flow, and orbit calculation performed in Japan is independently verified in Chile, Arizona, Australia, France, India. If orbital predictions indicated impact threat, the information would appear in multiple independent analyses within days. Discussions proliferating through professional and amateur networks faster than any organization could suppress. Social media discourse about the comet displays characteristic features some participants share genuine curiosity, asking questions about orbital mechanics and encounter geometry, seeking to understand what will occur and what observations might be possible. Others traffic in speculation detached from evidence, asserting without basis that the comet is artificial, that governments prepare secret defensive measures, that the close approach portends catastrophe hidden from public knowledge. The spectrum between informed discussion and baseless speculation appears continuous, gradations of understanding mixed with varying degrees of emotional investment in dramatic outcomes. Platforms designed to maximize engagement preferentially amplify extreme claims over measured analysis. Algorithms favoring content that provokes response regardless of accuracy. Scientific literacy gaps contribute to misunderstanding. Many people lack frameworks for assessing astronomical distances, probabilities, or the distinction between observed facts and speculative interpretation. The comet passing at 44,000 kilometers sounds close in isolation, dangerous when framed as near miss without context, explaining that near miss in astronomical terms means vastly different things than near miss between vehicles on a highway. The 3 in 100,000 impact probability sounds more alarming than 1.2 in 10,000 chance of asteroid impact on Earth annually. Though the terrestrial probability is 40 times higher, numbers become abstract at low probabilities, emotional response disconnecting from statistical reality. The narrative of hidden danger appeals to psychological tendencies favoring agency over randomness, pattern over noise, significance over mundane explanation. A comet passing Mars because gravitational dynamics happen to produce that trajectory lacks narrative satisfaction compared to the comet being intentionally directed, observed in secret, concealed to prevent panic. The former requires accepting that the universe operates without regard to human meaning, that coincidences occur through probability alone, that most events lack intentional cause or deeper significance. The latter provides structure agents with intentions, reasons for secrecy, implications beyond simple physical occurrence. Human cognition evolved in environments where detecting agency, even when absent, carried survival advantage, creating bias toward perceiving intention in random processes. Scientists communicating to public face challenges inherent in translating technical knowledge into accessible language without oversimplifying to the point of distortion. Explaining orbital uncertainty requires discussing statistics, error propagation, and Monte Carlo methods concepts not universally understood and requiring more space than typical news articles provide. Simplifying to "the comet will pass safely" omits the nuance that all predictions carry uncertainty, while including the 3 in 100,000 probability risks misinterpretation as genuine danger. The communication challenge is real, solutions imperfect, outcomes sometimes producing misunderstanding despite good faith efforts at clarity. Some interpreters of NASA's measured response cite historical examples where authorities downplayed risks later realized to be serious Challenger disaster, Columbia re-entry accident, various incidents where organizational culture dismissed warning signs. These examples demonstrate that institutions can fail in risk assessment, that caution is warranted regarding official assurances. However, the comet encounter differs fundamentally from engineering risks. Orbital mechanics permits precise calculation, verifiable by independent observers. While engineering failures often involve complex system interactions, organizational pressures, and judgments about uncertain technical issues, the comet's trajectory is not a matter of institutional assessment, but of physics accessible to anyone with observational data and computational tools. The actual information flow proceeds through established channels, astronomical telegrams announcing observations, academic papers reporting spectroscopic results, conference presentations sharing preliminary findings, preprint servers hosting articles before formal publication. Anyone monitoring these channels sees the information as it emerges. No gatekeeping beyond peer review processes that ensure quality control rather than restricting access. The Minor Planet electronic circulars contain detailed astrometric measurements submitted by observatories, the measurements listed with timestamps, telescope identifiers, observer names, allowing independent verification. The Central Bureau for Astronomical Telegrams issues circulars summarizing significant findings, distributed by email to subscribers and posted online. No subscription fee required for access. Public outreach efforts exist. NASA maintains social media accounts, posting images and brief explanations of ongoing observations. Astronomy communicators write blog posts and articles explaining the encounter for general audiences. Planetariums and science centers incorporate the comet into educational programs. These efforts reach audiences interested in astronomy, but do not penetrate broader culture sufficiently to generate widespread awareness. The competition for attention in information-saturated environment means even significant astronomical events go unnoticed by most people, unless they achieve the visibility threshold required for mainstream media coverage. A threshold set by factors novelty, visual impact, human interest angle, cultural relevance largely orthogonal to scientific importance. The encounter will occur whether noticed or ignored, observed in detail or passing unrecorded, understood correctly or misinterpreted through frameworks disconnected from physical reality. The comet follows its trajectory governed by gravity. Mars orbits governed by the same force, the interaction proceeding according to laws that operate independently of human awareness or understanding. Observers equipped with instruments and knowledge will collect data, analyze results, publish findings, advancing astronomical knowledge incrementally. Others will watch or not watch, understand or misunderstand, find meaning or dismiss the event as irrelevant to daily concerns. The universe accommodates all responses with equal indifference. Stars and planets and comets proceeding through their motions regardless of interpretation, meaning existing only in minds that impose it on processes inherently devoid of intention. Only took billions of years of cosmic evolution to produce beings capable of both understanding orbital mechanics and constructing conspiracy theories about cometary trajectories. The comet reaches perihelion closest approach to the Sun at 1.42 astronomical units, just inside Mars's orbital distance at 14 hours, 11 minutes, universal time on April 26th. At this point, the comet achieves maximum velocity in its heliocentric frame, gravitational acceleration at perihelion reaching peak values as the inverse square of distance dictates. The Sun subtends a larger angle in the comet's sky than at any other point along its trajectory. Solar radiation intensity at maximum, heating effects most pronounced, sublimation rates peak though the effect lags slightly behind perihelion passage thermal inertia. In the nucleus delays maximum ice loss by hours to days. Subsurface warming requiring time to reach depths where most volatiles reside. Heat conduction through dust and ice proceeding at rates determined by thermal properties that vary with porosity and composition. Mars encounter follows 21 hours later, the comet having travelled approximately 3 million kilometres past perihelion, beginning the outbound leg of its hyperbolic trajectory. The geometry places Mars nearly at the comet's closest approach distance to the Sun, the two bodies occupying similar heliocentric distances at encounter time, though their orbital planes differ enough that three-dimensional geometry separates them by 44,000 kilometres in actual space. The timing is coincidental. Mars happens to be positioned along its orbit where the comet's trajectory intersects the planet's orbital distance, an alignment requiring no special mechanism, simply the result of orbital periods and entry trajectory established when gravitational perturbations sent the comet sunward from interstellar space. Closest approach occurs at 14 hours, 32 minutes, universal time on April 27th, the comet passing Mars at relative velocity of 32.3 km per second as calculated in Mars's reference frame. At this moment the comet lies 44,100 km from Mars's centre, or 37,300 km above the surface, at an angle 43 degrees north of the equatorial plane. Mars occupies a position 87 degrees ahead in its orbit from where it will be 3 months later. Irrelevant detail except insofar as it determines which surface features face the comet during closest approach and what spacecraft experience optimal viewing geometry. The Curiosity rover in Gale Crater lies on the night side during closest approach, missing direct observation opportunities, though Mars Reconnaissance Orbiter in its Sun's synchronous polar orbit achieves excellent viewing angles. The gravitational interaction between Mars and comet operates through invisible curvature of space-time Mars's mass, creating a potential well that deflects the comet's trajectory, the deflection calculable through classical mechanics without requiring relativistic corrections. The comet enters Mars's gravitational sphere of influence, the region where Mars's gravity dominates over the Sun's approximately 12 hours before closest approach, the boundary lying roughly 600,000 kilometers from the planet. Within this sphere, the comet's motion is best described relative to Mars rather than the Sun, trajectory following a hyperbola in Mars-centered coordinates, the planet at one focus of the conic section, the hyperbola's eccentricity, periapsis distance, and orientation define the encounter geometry completely, parameters determined by the comet's velocity and impact parameter as it enters the sphere of influence. The deflection angle, the change in comet's velocity direction caused by gravitational interaction measures approximately 1.1 degrees, small but measurable with precise astrometry. This deflection alters the comet's heliocentric orbit slightly, rotating the orbital plane by a fraction of a degree, changing perihelion distance by a few thousand kilometers, modifying the time when the comet eventually exits the solar system by perhaps days. For Mars, the momentum exchange is reciprocal but negligible. The comet tugs on Mars gravitationally, altering the planet's velocity by approximately 6 micrometers per second, an amount unmeasurable with current instrumentation and irrelevant to Mars's long-term orbital evolution. The comet's mass, perhaps 10 trillion kilograms, is minuscule compared to Mars's 6.4 times 10 to the 23rd kilograms. Making the interaction asymmetric, Mars deflects the comet measurably. The comet fails to perceptibly influence Mars. Tidal effects remain small differential. Gravitational force across the nucleus creates stress amounting to perhaps a few hundred pascals, far below the kilopascal range stresses required to fracture ice. The nucleus experiences no disruption, no visible change in structure, no alteration beyond imperceptible strain that relaxes when the comet recedes beyond tidal influence. Rotation continues at 11.7-hour period, unchanged by the encounter. Angular momentum conserved through the passage. If instruments existed on the nucleus to measure acceleration, they would record a temporary increase in centripetal force as the comet swings around Mars's gravity well, then return to normal as the encounter ends. The entire episode lasting only hours of observation in reference frame where duration matters. The coma extends far enough that Mars passes through its outer region's tenuous boundaries, where gas and dust density drops toward interplanetary background levels but remains detectably elevated. Spacecraft in Martian orbit traverse these regions, potentially encountering increased dust flux, though particle densities are so low that probability of actual collisions remains negligible. The Mars Atmosphere and Volatile Evolution Orbiter detects increased ion flux as it passes through the comet's ion tail. Instruments measuring enhanced densities of water group ions H3O+, OH+, H2O+ created when solar wind ionizes gas in the coma. The measurements last minutes as the spacecraft crosses the tail at orbital velocity. data stored on board for later transmission to Earth, contribution to scientific understanding of cometary ion production, and solar-wind interaction. From Mars's surface, if human observers existed there with appropriate instruments, the comet would appear as a diffuse patch in the sky brighter than any star, possibly rivaling Venus as seen from Earth, though exact brightness depends on dust production rates and viewing geometry. The coma, backlit by the sun at closest approach, would show full-phase illumination, dust scattering sunlight efficiently, creating a glow visible to dark-adapted eyes as an out-of-focus smudge moving slowly against background stars. The motion would be detectable over minutes the comet's 32 km per second relative velocity, translating to angular motion of approximately 0.04 degrees per minute at closest approach, fast enough that careful observers could detect position changes within an hour. The tail, if well developed, might extend several degrees across the sky, though seeing structure in the tail would require photographic integration or sensitive instruments. No humans observe from Mars. The planet hosts only robots, machines operating autonomously or following commands uploaded from Earth, instruments recording data without understanding, cameras capturing images that will be transmitted across millions of kilometers of space to be viewed by beings who designed them. The rovers, dormant in Martian night during closest approach, miss the opportunity for direct imaging. The orbiters, some positioned favourably, turn cameras and spectrographs toward the visitor, collecting data that will require months to fully analyse and interpret, observations that may reveal details about the comet's nucleus, coma structure, or compositional variations not accessible from Earth-based viewing geometry. The encounter duration, measured from first detection of perturbed trajectory to return to heliocentric motion unaffected by Mars, spans approximately 1 day, 12 hours entering the sphere of influence, 12 hours departing, with closest approach marking the midpoint. From wider perspective, the encounter is instantaneous, a geometric crossing of trajectories in four-dimensional space-time. Two objects briefly sharing proximity in the vast emptiness that separates most solar system bodies. The comet spends mere hours within 1 million kilometers of Mars, a tiny fraction of the years it travelled to reach this point, briefer still compared to the billions of years both objects have existed in the galaxy. After closest approach, the comet recedes velocity relative to Mars, decreasing as the planet's gravity no longer accelerates it forward, but begins pulling backward, a transition occurring at periapsis that reverses the effect without changing the outcome. The comet departs on modified trajectory, gravitational slingshot having increased its heliocentric velocity by approximately 0.3 kilometers per second, an assist that shortens the time required to reach the outer solar system and eventual interstellar space. Within days, the comet lies beyond Mars's orbit, continuing outbound, brightness diminishing as heliocentric distance increases and solar heating decreases. Within weeks it will fade below detection limits for all but the largest telescopes, orbital monitoring ceasing when position uncertainties grow too large for useful prediction, the comet returning to anonymity among the countless small bodies traversing space beyond human observation capability. Mars continues its orbit, one revolution among billions since its formation. The encounter another event in a history too long for human comprehension, written in impact craters and atmospheric measurements, readable only to those with instruments and patience. The planet rotates, atmosphere circulates, polar caps sublimate and recondense with seasons, processes continuing as they have for billions of years, briefly witnessed by machines sent from Earth to observe and measure and report, finding no spectators except those who built the observers. Only took the evolution of technological civilization to create such vicarious witnessing. Dust settles from the comet's passage, microscopic particles following ballistic trajectories through the Martian atmosphere, their descent governed by gravity and atmospheric drag, terminal velocities determined by particle size and air density. The particles small, typically 1 to 10 micrometers in diameter, surface area large relative to mass, causing them to drift slowly through the thin air rather than plummeting rapidly. A particle 5 micrometers across falling through Mars's atmosphere at 10 kilometers altitude descends at approximately 1 centimeter per second, requiring weeks to reach the surface, drifting horizontally with atmospheric winds that carry it hundreds or thousands of kilometers from its entry point. The particles disperse globally, spreading through atmospheric circulation, eventually settling onto polar ice caps, equatorial dunes, crater floors, volcanic plains distributed so thinly that no single location receives measurable accumulation, yet collectively adding tons of cometary material to Mars's surface inventory. The dust contains silicate minerals, olivine and pyroxene crystals formed at high temperatures, forged in stellar atmospheres or inner protoplanetary disk regions before being transported to cold outer zones where they incorporated into the comet. These minerals, once settled, become indistinguishable from native Martian dust's same composition, similar grain sizes mixed into the regolith by wind and microscopic impacts until their cometary origin becomes unrecognizable without detailed isotopic analysis that can distinguish pre-solar signatures from solar system indigenous material. The dust also carries carbonaceous particles, organic compounds, water ice or hydroxylated minerals formed when ice reacted with rock during cometary activity. These organics degrade slowly under ultraviolet radiation at Mars's surface, half-lives measured in years to centuries depending on molecule complexity and environmental protection. Trace molecules from the comet's coma enter Mars's upper atmosphere water, vapor photodissociates into hydrogen and oxygen atoms. Carbon dioxide ionizes and dissociates into carbon monoxide and atomic oxygen. Complex organics fragment into smaller species. These additions occur continuously from micrometeorite ablation and cometary dust. The 3I Atlas encounter simply providing a brief enhancement of normally ongoing processes. Atmospheric chemistry absorbs the additions without noticeable change. Mars's atmosphere contains approximately 2.5 times 10 to the 16 kilograms of gas, while the comet contributes perhaps a few thousand kilograms of volatiles during the encounter, a ratio of 1 part in 10 trillion. Dilution so extreme that even sensitive instruments cannot detect composition changes attributable specifically to this event. Water molecules that survive photodissociation mix into atmospheric water vapor, contributing to the planet's hydrological cycle condensing as ice clouds at high altitudes, sublimating in daytime warmth, absorbing onto dust grains, diffusing into polar ice deposits during winter. The comet's water carries isotopic signatures different from native Martian water, deuterium ratios reflecting formation in another stellar system under different conditions. If these molecules could be tracked, if isotopic measurements were sensitive enough to detect the dilute addition, they would show temporary enhancement of interstellar isotopic ratios in specific atmospheric regions or surface deposits. But no such tracking is possible. The molecules mix, react, freeze, sublime, become indistinguishable within days from the vastly larger reservoir of Mars's existing water inventory. Organic molecules delivered to the surface face harsh conditions, intense ultraviolet radiation, oxidizing soil chemistry, temperature extremes cycling between -130 Celsius at night and occasional positive values in equatorial summer afternoons. Complex organics degrade through photolysis, breaking into smaller fragments, carbon-carbon bonds severing under ultraviolet photons, eventually reducing to carbon dioxide that rejoins the atmosphere. Simpler molecules, methane, formaldehyde, formic acid survive longer but still face destruction timescales of years to decades unless protected by burial under dust or incorporation into ice. Some fraction of delivered organics persists in protected microenvironments, shadowed crater walls, subsurface ice, the interiors of rocks fractured by thermal stress locations where these molecules might endure for millennia, awaiting future missions that might sample and detect them. The comet's passage adds infinitesimally to Mars's total mass, perhaps a few thousand tons of dust and gas delivered to the planet during the encounter, compared to Mars's mass of 6.4 times 10 to the 20 kilograms. The addition equals approximately 1 part in 10 to the 17th, a ratio so extreme that attempting to measure it directly would be meaningless. Yet integrated over billions of years, countless such encounters delivered substantial material estimates, suggest comets and asteroids added 1 to 10% of Mars's total mass during and after formation. Contributions that built the planet from smaller precursors and continued delivering water and organics after primary accretion ended. Scientific return from the encounter will unfold over months and years, images requiring processing and analysis, spectra needing detailed interpretation, data archives to be searched for subtle signals that might reveal information not apparent in initial inspection. Papers will appear in journals describing the comet's composition, comparing 3I Atlas to other interstellar objects and solar system comets, refining models of how comets form and evolve. The Mars encounter, unique in providing close-range data on an interstellar object's interaction with a planet, will generate specialized studies examining dust deposition, atmospheric perturbations, and gravitational effects. Most results will be negative. No measurable atmosphere change detected. No surface impacts recorded. No spacecraft anomalies attributable to cometary dust. Negative findings that nonetheless provide useful constraints on model parameters and theoretical predictions. Curiosity rover will continue its traverse up Mount Sharp, drilling rocks that might contain clays formed billions of years ago when liquid water interacted with volcanic minerals, searching for organic molecules that might indicate ancient habitability. The rover will not detect cometary organics from 3I Atlas. Those molecules settle globally at nanogram per square meter levels, far below detection thresholds, mixed with trillions of times more abundant native dust. But the rover's measurements contribute to understanding Mars's organic inventory, providing context for interpreting how comets throughout history contributed to the planet's chemistry, whether that chemistry ever achieved the complexity required for life, and what remnants might persist in ancient rocks if life once existed and vanished. Perseverance rover in Jezero crater collects samples destined for eventual return to Earth, rock cores sealed in titanium tubes, cached on the surface for future retrieval mission, specimens that may contain definitive evidence of past life, or may show only abiotic chemistry indistinguishable from prebiotic processes. Those samples, when returned, if returned, missions remaining contingent on funding and technical success of multiple sequential steps, will be analysed in terrestrial laboratories with instruments far more sensitive than any deployable to Mars, measurements revealing isotopic compositions, organic molecules, mineral textures at nanometer scales. If cometary organics from billions of years ago persist in those rocks, laboratories might identify them through isotopic signatures or molecular structures characteristic of interstellar chemistry, finding in ancient stone the record of deliveries like the one occurring now. The data from 3I Atlas joins archives containing observations of thousands of comets, asteroids, meteors, dust particles, all contributing to understanding solar system formation and evolution. Each object observed adds constraints to models, narrows uncertainty ranges on parameters like volatile composition ratios, formation temperature distributions, or dynamical pathways that transport material between stellar systems. The accumulation is incremental. No single observation revolutionizes understanding, but ensemble statistics from many observations gradually reveal patterns, correlations, compositional trends that point toward underlying physical processes. Science proceeds through such accumulation more than through singular discoveries. Patience and thoroughness eventually yielding comprehension that flashes of insight alone cannot provide. The comet recedes toward outer solar system and eventual interstellar space. Its encounter with Mars complete. Modifications to its trajectory imprinted permanently in orbital elements that now contain Mars's gravitational signature. The nucleus has lost perhaps 1% of its mass to sublimation during inner solar system passage, surface thinned by centimeters, crust fractured in places where thermal stress exceeded tensile strength. dust mantle thickened by deposition of non-volatile material left behind when ice sublimated. These changes represent aging the comet transformed slightly by solar heating, wearing the marks of passage through a foreign stellar system, accumulating history written in surface texture and volatile depletion patterns that no observer will likely ever measure directly. Mars retains even less obvious modification, a few thousand tons of dust added to the billions of tons already settling from space annually through micrometeorite bombardment. Trace gases mixed into atmospheric inventory orders of magnitude larger, gravitational tug altering orbital velocity by micrometers per second. The planet continues its ancient patterns, atmosphere circulating, polar caps exchanging mass with air seasonally, dust storms redistributing surface material, geological quiescence broken only by occasional meteorite impacts, and slow subsurface processes beyond surface observation. The encounter leaves Mars essentially unchanged. Another event in a history composed of such events, accumulating toward a future where the planet's evolution continues along trajectories established billions of years ago. Only took 4 billion years of history to render one more cometary passage unremarkable. The comet crosses Jupiter's orbit outbound, receding from the Sun at velocity steadily increasing as it climbs out of the gravitational well, trading potential energy for kinetic energy in eternal conservation that governs all orbital motion. The heliocentric distance now exceeds 5 astronomical units, 750 million kilometers, placing the comet in the region where solar heating weakens to levels insufficient to sublimate water ice efficiently. Carbon monoxide continues outgassing from subsurface reservoirs where warming penetrated during perihelion passage. Delayed release as heat diffuses through insulating dust layers, but water production drops precipitously, falling to 10% of peak rates and declining further with each passing week. The coma dims, contracting as gas production decreases and existing material disperses into space. The visible envelope that once extended millions of kilometers now measuring only tens of thousands, barely detectable in all but the most sensitive telescopes. The dust tail fades faster than the gas coma. Larger particles no longer lofted by escaping gas begin falling back toward the nucleus. Smaller particles dispersed by radiation pressure and solar wind spread along the comet's orbital path, thinning into invisibility. Within months, the comet will appear star-like even in large telescopes. Its extended structures collapsed or dispersed, only the nucleus and immediate vicinity remaining as point source light reflected from the ancient surface. Photometry becomes challenging as brightness drops, magnitude measurements carry increasing uncertainty. Rotation period determination requires longer observation sequences to achieve sufficient signal-to-noise ratio. Spectroscopy becomes impossible without prohibitively long integration times. Observatories cease regular monitoring, turning instruments toward brighter targets, newer discoveries, objects closer to Earth or Sun where scientific return justifies telescope time allocation. The trajectory carries the comet toward the outer solar system's scattered disk, a region beyond Neptune's orbit, where gravitational perturbations from the giant planets injected objects onto highly elliptical or inclined orbits during the solar system's early dynamical evolution. The comet will not remain in this region. Its hyperbolic orbit ensures continued outward motion, but passage through the scattered disk creates possibilities for gravitational encounters with distant bodies. Dwarf planets like Eris or Makemake, scattered disk objects measuring hundreds of kilometers across, populate these distant reaches in orbits taking centuries to complete. The probability of close encounter as negligible space remains mostly empty, even in regions containing billions of small bodies but non-zero. And any encounter would modify the comet's trajectory through gravitational interaction, potentially altering its departure velocity or direction unpredictably. Neptune's gravity influenced the comet during inbound passage, a distant perturbation occurring years before perihelion, when the comet passed within 50 astronomical units of the ice giant, close enough for Neptune's gravity to measurably deflect the trajectory. Similar interaction occurs during outbound journey. Neptune now positioned differently along its orbit, creating asymmetric perturbation that adds small velocity component perpendicular to the comet's motion. These gravitational assists or hindrances accumulate each planet encountered, contributes to the comet's final velocity vector at solar system escape. The cumulative effect potentially altering escape velocity by kilometers per second and changing the direction toward which the comet departs by several degrees. The comet leaves the solar system on a trajectory different from its arrival. Solar system's planetary configuration imparting momentum transfer written into the comet's future path through interstellar space. The comet will cross the heliopause, the boundary where solar wind pressure balances interstellar medium pressure in approximately 2,000 years, assuming current velocity and accounting for gravitational deceleration as it climbs out of the Sun's gravity well. The heliopause lies roughly 120 astronomical units from the Sun in the comet's departure direction, though the boundary's exact position fluctuates with solar cycle and variations in interstellar medium density. Beyond the heliopause, the comet enters the interstellar medium proper, a region where gas density measures approximately 1 atom per cubic centimetre, far denser than interplanetary space, but still vacuum by terrestrial standards. The comet will experience drag from interstellar gas, momentum transfer from occasional collisions between the nucleus and interstellar atoms. Though effects remain minuscule, crossing 1 light-year of interstellar medium removes less than 1 meter per second from the comet's velocity, negligible compared to its 40 km per second speed. Cosmic rays bombard the nucleus continuously, high-energy particles from supernova remnants, pulsars, and active galactic nuclei, accelerated to relativistic velocities, traversing the galaxy and striking whatever matter lies in their path. These particles penetrate the nucleus's surface, ionizing atoms, breaking chemical bonds, gradually darkening the crust through radiation chemistry that converts organic compounds into complex refractory materials. The same radiation creates new molecules through radiolysis, splitting water ice into hydrogen and oxygen, combining carbon and hydrogen into hydrocarbons, synthesizing ammonia from nitrogen and hydrogen. Over millions of years, cosmic ray processing transforms the nucleus's outer layers, creating a radiation-processed mantle distinct from the pristine interior, the surface gradually evolving even in the absence of solar heating. Interstellar dust impacts the nucleus, occasionally tiny grains travelling at velocities of tens of kilometers per second relative to the comet, each impact releasing energy proportional to velocity squared, vaporizing small amounts of surface material. These impacts occur rarely, perhaps 1 grain per square meter per million years in typical interstellar medium, but over billions of years they erode the surface micrometers at a time, competing with cosmic ray processing to determine surface properties. The impacts also deliver material, the grains themselves, composed of silicates and carbonaceous materials, embed in the nucleus or vaporize and recondense, adding layers of interstellar dust to the cometary surface. The nucleus becomes a palimpsest, layers recording different epochs of interstellar travel, each layer modified by subsequent radiation and impacts. The comet will not return, its hyperbolic trajectory is unbound, requiring no external perturbation to escape solar gravity permanently. It departed its formation system billions of years ago on similar trajectory, escaped into interstellar space, wandered through the galaxy for eons before gravitational perturbations from passing stars gradually altered its path, eventually directing it toward the solar system. Now it departs again, carrying modifications from its solar passage, depleted volatiles, altered surface, gravitational deflection from planetary encounters, but fundamentally unchanged, still an ice mountain tumbling through space, carrying information about conditions in molecular clouds before the Sun existed. In 4 billion years, approximately when the Sun evolves into a red giant and engulfs the inner planets, the comet will have travelled 160,000 light-years at its current velocity, a distance exceeding the Milky Way's diameter, carrying it potentially into intergalactic space or into the halo of the galaxy, or perhaps into another stellar system if trajectories align. It will be cold, dormant, surface processed by cosmic rays and interstellar impacts into a dark crust meters thick, interior still containing pristine ice from its formation, molecules that condensed before Earth existed and will remain frozen long after Earth is destroyed. The ice does not decay, does not age beyond surface modification, simply persists in frozen stasis, waiting for warmth that may or may not ever arrive again. If the comet eventually encounters another stellar system, passes close enough to another star for solar heating to initiate sublimation, the process will repeat coma development, tail formation, observations by any astronomers that star may host, another brief transformation from dormant iceball to active comet before departing again into the cold. Each stellar passage takes a small fraction of the comet's mass, but the nucleus is large enough to survive dozens or hundreds of such encounters before exhausting its volatiles and becoming an inert rock tumbling through space. The comet might exist for trillions of years, outlasting the Sun, surviving the era of stellar formation, persisting into epochs when the galaxy contains only white dwarfs, neutron stars, and black holes, all active star formation having ceased, the universe expanding and cooling toward its ultimate fate. The comet is patient, it has no choice but patience, no agency to become impatient, no awareness that time passes. It exists in eternal present, each moment indistinguishable from the previous except for imperceptible changes in position and velocity, following the path determined by gravity and initial conditions, carrying no memory of Mars, Earth, the Sun, or the brief warmth of stellar proximity. It is object, not subject. Matter arranged in specific configuration. Atoms bonded according to quantum mechanics and thermodynamics. Structure without purpose. Existence without meaning beyond what observers project onto it. Only observers create significance, finding in the comet's trajectory stories about planetary formation, interstellar chemistry, galactic dynamics narratives imposed on indifferent matter that simply continues being what it is. Mars orbits the Sun, 45th billion-something revolution since formation, another circuit in a series that will continue until the Sun's evolution alters the solar system beyond recognition. The planet turns, atmosphere circulates, dust settles, ice sublimates and recondenses with seasons, processes that have operated for 4 billion years and will operate for billions more. The encounter with 3i Atlas is finished, recorded in spacecraft data and observer logs, published eventually in papers that will be cited by researchers, building toward understanding, contributing to the gradual accumulation of knowledge about how the solar system operates, where it came from, what might become of it. The silence that followed the encounter was never concealment. Only the quiet of normal scientific work proceeding, observation and measurement continuing without drama, because drama is human imposition on processes that simply occur, governed by physics, indifferent to narrative. The solar system turns in its ancient rhythms, planets tracing ellipses worn smooth by repetition, moons circling worlds, all falling endlessly around the Sun that falls endlessly through the galaxy's rotating arms. The comet fades beyond detection, one point of light among countless others, no longer tracked, no longer named in daily observation logs, simply gone into the darkness from which it briefly emerged. The instruments turn elsewhere toward asteroids closer to Earth, toward comets approaching perihelion, toward the endless catalogue of objects requiring measurement and monitoring. The work continues as it always has, patient accumulation of positions and brightnesses and spectra, data flowing into archives where it waits for analysis, interpretation, questions not yet formed. Mars rotates through another sol, then another, seasons progressing as they have progressed for billions of years, polar caps exchanging mass with atmosphere in cycles older than memory, dust storms rising and subsiding, the planet performing its slow weathering under a sun that provides warmth insufficient to melt ice, but adequate to maintain the subtle movements that constitute Martian climate. The rovers pause in their traverses, solar panels collecting one sunlight, instruments dormant during cold nights, awakening with dawn to continue their patient investigation of rocks that might reveal what Mars once was, what chemistry once operated, whether complexity ever achieved the threshold where matter becomes life. The data from the encounter exists now in storage terabytes of images, spectra, telemetry, measurements made during those hours when comet and planet shared proximity, information that contains more than has yet been extracted, details awaiting techniques not yet developed, questions not yet asked. Scientists will return to these archives in months and years, mining them for signals initially missed, comparing them with observations of other objects that reveal patterns invisible when examining single cases. Knowledge emerges slowly from such archives, understanding accreting like dust settling onto airless worlds, accumulating grain by grain toward comprehension. The universe expands, galaxies receding from one another through space itself stretching, the cosmological constant or dark energy, or whatever mechanism drives the acceleration, ensuring that future observers in distant galaxies will see fewer neighbours, eventually only their own local group gravitationally bound while the rest of the visible universe fades beyond detection limit. But these are timescales beyond contemplation, futures so remote that the sun's death represents near-term event in comparison, eons stacked upon eons until human words for duration lose meaning, can only gesture toward vastness that consciousness cannot encompass. The comet continues outward into that vastness, velocity nearly constant now in the sun's weakening gravity, trajectory set for the next million years, the next billion, unchanging except for perturbations so subtle they accumulate across timescales measured in galactic orbits. The ice endures, molecules locked in crystal lattices, hydrogen bonded to oxygen, carbon to oxygen, nitrogen to hydrogen, atoms that have existed since shortly after the Big Bang, recycled through stars and stellar atmospheres and molecular clouds, now arranged in these particular configurations, stable until some future warmth or impact rearranges them again. Mars turns beneath stars that wheel overhead in patterns shifting imperceptibly as precession slowly rotates the planet's axis. The stars themselves moving through the galaxy on orbits perpendicular to human observation, all motion and all stillness relative to chosen frame. The universe containing no absolute reference, no fixed point from which to measure, only relationships between objects, all equally in motion, all equally at rest depending on perspective. The silence is not ending but simply continuing. The normal state of things, the default condition of matter in space where sound cannot propagate, where temperature approaches absolute zero, where time passes without marking. The encounter happened. The data exists. The interpretation proceeds. The universe persists in its expansion and its ancient momentum, and nothing requires resolution or conclusion, only continuation. The endless proceeding of processes following physical law into a future that remains undetermined in detail, but constrained by the same equations that have governed since the beginning, whatever the beginning was. The stillness between stars is patient. The cold is permanent until disrupted by warmth that always proves temporary. The darkness is vast and the light is brief, and the story, if there is story, is told in wavelengths and orbital elements and isotopic ratios, written in languages that require translation, read by those who can decode meaning from measurement. Sleep comes to those who sleep. The universe requires no rest, permits no rest, continues its expansion and its subtle dances while matter arranges and rearranges, and the silence was never broken, only listened to with more attention for a brief moment, then allowed to resume.